Good to see you. And introduce yourself before you dive in, and then we can get going. And excellent talk last week at the GDC meeting. So
thanks, Mark. Yeah. So yeah, I guess I'll just kick off. And by the way, before I get started, I'm going to try to monitor the chat. I'm kind of looking at it on my other screen here. So if I look like I'm looking off to the side, that's why. But yeah, so I'm Mike Hartinger. I'm a research scientist at Space Science Institute. And I've known Mark for many years, going back to grad school. So it's great. And actually, I went to this summer school, I guess, I don't know, I think it was the first one ever back in 2009. So it's awesome to be here again and seeing everyone virtually. And I know everyone's going to enjoy it. Those who are going to Boulder later on will very much enjoy it, I think. So yeah, I'm Mike Hartinger, Space Science Institute. And I mostly study the Earth's magnetosphere and the near-Earth space environment, both from the ground and in space. But today I'll be talking to you about the global structure of the magnetosphere. And I'm going to try to not be as biased towards the Earth for those who are studying other magnetospheres, and talk about some basic principles. And before I get started, I just want to acknowledge that I took a lot of material from past lectures that are on the summer school website from Pran Bagnall, Frank Toffoletto, and Nicholas Achilleos. So you'll see a lot of acknowledgements there from them. So let me put this full screen so you can see a little better. And I just swap this. Okay. Yeah, so let me get to the first slide. So again, today I'll be just talking about high-level introduction to the key factors controlling the structure of planetary magnetospheres, with a bit of a focus on the Earth's magnetosphere, but looking at other ones as well. And I just wanted to see real quick if people could raise their hand if they're studying, who here is studying the Earth's magnetosphere? If you can raise your virtual hands. And hopefully I can see that. Okay, good, I see it. Yeah, so a lot of people studying the Earth. Very good. Okay, so we got a lot of Earth people here. And then let's also see, let me go to the next slide here. If you're studying another magnetosphere, could you put it in you could either raise your hand or could you put it in the chat? I'd be curious just to see if, who's studying. Okay, we got Mars, people studying the Mars and Venus. Oh, Uranus, very nice. Yeah, so Jupiter, very nice. So good variety. Jupiter in the context interacting with Europa. Okay, great. Jupiter, yeah, great. So always good to have people studying multiple. So some people are studying more than one magnetosphere, which is great. So you'll get hopefully in the lecture today, you'll have a bit of everything. Like I said, I'm gonna try to cover other magnetospheres, not just Earth. So we'll get to some of the basic factors that affect all magnetospheres. And then as far as references or further reading, I think you already got some of this, the chapters in the textbook that might be useful. Also, you can download the previous lectures that I'm getting material from, and I'll definitely encourage you to look at these lectures as well as others on the website. There's a lot of great material there, especially from some of the stuff that I'm not going to have time to cover, because 15 minutes is way too short to cover everything about the structure of planetary magnetospheres. But then also, I use a lot of material, just not directly in the slides, but for my own knowledge from grad school, from this textbook, Gibbelson and Russell. So some of the ideas you see here will be drawn heavily from there, but they're common to other textbooks as well. Okay, so what is a magnetosphere? So I pulled this definition right from the textbook that you all have from the summer school. The quote is that the magnetosphere is then the region of space around the central object within which the object's magnetic field has a dominant influence on the dynamics of the local medium. That's a mouthful, but it's basically saying that if an object, whether it's a moon or a planet or whatever, has a magnetic field, the region that's dominated by that magnetic field in terms of the dynamics of the plasma is basically the magnetosphere. And so like in the context of the Earth, the region out to the outer boundary here where the dynamics are dominated by the Earth's magnetic field is the Earth's magnetosphere. And then you have Other planets, of course, have a similar thing going on with, like Saturn, Jupiter. Any of those planets have a big magnetosphere, but not every planet has a magnetosphere. And there's a bit of a fuzzy definition here, but oftentimes people talk about like Venus, for example, and since it doesn't have an internal magnetic field, or at least not a very strong one, it doesn't really have a magnetosphere in the same sense we think of it as at Earth, for example, or Mercury or some of the other planets. And some moons have magnetospheres. Of course, moons of Jupiter will have magnetospheres. So there's a lot of variety, as we'll see in today's talk, of types of magnetospheres. And one thing I'm not going to cover, because I saw someone was studying Mars, is this idea of the mini magnetospheres, where you have these little pockets of magnetized areas on the surface of different planets that can kind of act like a magnetosphere. So that's a very interesting topic, but unfortunately, I'm not going to cover it in detail today. But some of the basic principles will still apply to that concept. So yeah, the big factors I'll be talking about today are that control the global structure of the magnetospheres are the ambient medium. Usually in the talk, when I say ambient medium, I mean the solar wind. But there are moons like Jupiter where the ambient medium is actually Jupiter's magnetosphere for the moons of Jupiter. But I'll be focusing mostly on solar wind today. Also be talking about the properties of the object's magnetic field. That's another very important thing that it controls the structure. And for example, the magnetic field strength. And I'll just pause for a second here and just ask, as far as magnetic field controlling the structure of magnetosphere, can anyone think of other things besides the strength of the magnetic field that might affect the structure of magnetosphere? Any thoughts? Just throw them in the chat. Awesome. Yeah, lots of great comments. Yeah. So the order, so the number of moments, is it dipole or is it quadrupole or whatever? Interaction with moons, yes. Planet's atmosphere, yes. Rotation speed, yeah. Crustal B field, yep. Orientation, yes. So I'll get into a lot of these things that you're mentioning later on. So this is a great ideas, great thoughts. Yeah, the orientation is crucial. You'll definitely see that later on with Uranus. And I saw someone who I think was studying Uranus or Neptune, and very important there. So all great thoughts, all great comments. And then someone mentioned the rotation rate, very important, object's rotation rate and rotation axis, and properties of the object's atmosphere. Someone also mentioned that. So yes, all these things are very important, and I'll be talking about them today. So let's get into the first one. And again, this is biased towards solar wind planetary magnetospheres. So there are other things that I'm not going to talk about, like the ambient medium at Jupiter, for example, for the moons of Jupiter. But a lot of this is a basic thing, though, for a lot of the magnetospheres that we focus on in the heliosphere, and that's the concept of the shocks that form upstream of the magnetospheres. So here you have the region. This could be like Earth, for example, and the region dominated by the Earth's magnetic field. The outer boundary, by the way, that I'll talk about this on the next slide, is the magnetopause. But upstream of that boundary, you have a shock that forms, and that's because the solar wind flow is supersonic. So you need a shock to form to basically tell the solar wind that there's an object ahead of it. And in the shock, you're going to have kinetic energy converted to thermal energy, and the flow is going to be basically diverted around the obstacle. If the solar wind wasn't supersonic, you wouldn't necessarily, or you wouldn't have this kind of feature, but it's ubiquitous, in Earth, Jupiter, other planets as well. And I'm not going to talk about shock physics in detail. I just wanted to mention it at least once, and I'll direct you to Frank Toffoloto's lecture. And actually, there's other lectures as well that talk about shocks. But it's a very important feature, and the region between the shock and the magnetopause, the transition region, is also very important for a lot of the dynamics, and I'll briefly mention that later on. Okay, so this slide here will get you pretty far in terms of understanding the structure of a magnetosphere as far as how big it is, and that's the concept of pressure balance. So I'm guessing most of you are familiar with MHD, and if you're not, there's definitely some lectures that go into more depth on it, and also some of those references I put up earlier. But if you're not, just know that there are various pressure terms that have to do with the solar wind, basically the momentum flux of the solar wind that's wants to push on the medium's magnetic and thermal pressure. And then on the other side, you have a pressure exerted by the magnetic field, the magnetic pressure. And at the Earth's magnetosphere, these two, when these balance and are in equilibrium, that basically tells you where the magnetopause boundary will be, more or less. And this is, by the way, a lot of material from Achilleos' 2015 lecture, but basically you can write down a proportionality between the radius of the magnetopause and the solar wind dynamic pressure, that pressure that the solar wind is basically pushing on the magnetosphere with. And there's a current system exactly at the magnetopause, current sheet, that forms in response to this pressure balance. And so when the pressure from the solar wind is increased, you're going to have the current dynamically changing, and until these two come into equilibrium again. Now I'll just kind of allude to this for the next couple of slides. I'll be talking about the fact that this pressure balance will get you pretty far, but there's another term, the thermal pressure, that's also can be important, although it's not that important at Earth. And so just let's go on to the next slide and see that a little more. So these couple of slides are going to be from Fran Bagenal, and I really like them because they kind of lead you down the path of trying to understand what's going on at some of the other planetary magnetospheres and why there are some pretty key differences between, for example, the Earth and Jupiter. So this slide basically writes down a nice expression that tells you, based on that pressure balance, where the magnetopause is relative to the radius of a planet. So in order to do this, to have this equation, you need to know the solar wind dynamic pressure where the planet is. So as you move out in the solar wind speed is sort of constant. For example, as you move from Earth to Jupiter, it doesn't change that much. The solar wind density, though, does decrease quite a bit. And of course, the magnetic field of different planets is different. So Jupiter has a much stronger magnetic field than the Earth, and I'll show that on the next slide. But you can write down this equation, and immediately you're going to see that the magnetopause location relative to the radius of the planet is quite different between different magnetospheres. And that's what's shown on this slide, again, from Fran Bagenal, that, first of all, you can look at the surface magnetic field, which gives you an indicator of how strong the magnetic field is at these different planets. And Mercury has a much weaker magnetic field than Earth, which has a much weaker field than Jupiter. And so that all feeds into this equation. And also, again, that solar wind density change also feeds into that equation. As you move out in the solar wind, the density goes down. So this is what you get if you calculate, using that pressure balance, the magnetopause location relative to the radius of the planet. And you see that at Mercury, it's a tiny fraction, or it's not a tiny fraction, but it's a fraction of a Mercury radius. So the magnetopause is very close to Mercury, at Mercury's magnetosphere. It's very close to the surface of the planet, only about 0.4 Mercury radii out. At Earth, it's about 10 Earth radii out, more or less, on the day side. At Jupiter, this equation predicts that it's 46 Jovian radii out because of that much stronger magnetic field and the weaker density. And Saturn 20, Uranus 25, Neptune 24. Okay, then if you look at what you actually measure, though, you see there are these ranges, and these ranges of values have to do with the fact that the solar wind is changing with time, and so it can be more or less pressure exerted, so that basically that magnetopause can move in and out as you exert more or less pressure. So that's where these ranges come from. But interestingly, and Fran is highlighting this here, the radius of Jupiter, or the magnetopause of Jupiter, is actually much further out when you look at observations than this equation would predict, and the same at Saturn. And Uranus is an oddball that I'll talk about later. But just focusing on these two, there's a good reason for this, and that, as I was alluding to, is that it's not just the magnetic pressure, it's also the thermal pressure that matters. Jupiter and Saturn have hot plasma that can contribute quite a bit to that pressure balance. So when you talk about pressure balance at Jupiter and Saturn, you have to consider the thermal pressure of the planetary magnetosphere, the hotter plasma that actually goes all the way out to the magnetopause, and can be an important term to understanding where the magnetopause is going to be located. And I like this figure too, because it starts to put into context how big these different magnetospheres are. So this green circle, this is the Earth's magnetosphere. This green circle is kind of giving you the typical magnetopause location on the Earth-Sun line, for example. And then you can translate that to Saturn's magnetosphere, and you see it's really tiny because, of course, Saturn is huge. It's a gas giant, but also because Saturn's magnetosphere is much larger relative to the Earth because of the stronger magnetic field and also the thermal pressure. And then you can then do this again and go to Jupiter and see that Saturn's magnetosphere is actually quite small compared to Jupiter, which tells you that Earth is like ridiculously small compared to Jupiter. And so this is just putting it into scale here, that there is a big variety of magnetopause sizes and a big variety of already different factors that are going to control the global structure of magnetospheres. So some planets, like Jupiter and Saturn, you need to consider both the magnetic and the pressure, balancing the solar wind pressure when you talk about the size of the magnetosphere. Other planets like Earth, you don't really care as much about the thermal pressure most of the time. And then this is just a schematic again from Van Bagenal of Jupiter's magnetosphere, showing basically some of the reasons you might expect the planet to be a bit different than Earth. One big one, of course, is that you have these planets, these moons of Jupiter that are putting out a huge amount of plasma with different properties than you would have at the Earth. And there's other reasons as well, but you'll see another cartoon later that compares something like Jupiter to something like Uranus or Neptune, which is even wackier and for other reasons because of the magnetic field orientation and so on. But this is the equation I probably should have started with, and this is the one that you will see if you go to a textbook like Kivelson and Russell or the summer school textbook. You have to, if you don't know anything about the magnetosphere to start with, you should always write down the pressure balance as having to do with the solar wind pressure, the magnetic pressure, and the thermal pressure term, which can be very important. And one last thing I'll say, if you're looking at the magnetosphere of a moon, you might also have to change this side of the equation because there's going to be different pressure balances to consider when you're not in the solar wind with this big, bulk flow of plasma hitting you. Okay, so pressure balance gets you really far in terms of figuring out the size of magnetosphere, especially in an equilibrium sense. But when you start wanting to look at things like how stretched is the tail or the other side of the magnetosphere away from the sun, and the internal structure of magnetosphere, you have to consider other processes. And reconnection is one of those processes. And so the next couple of slides, I'll be talking about the solar wind magnetosphere interaction in the context of reconnection. So I'm not going to, again, it's a short lecture, so I'm not going to go into the depth on what reconnection actually is because there's not enough time. But I'll say that it's covered quite extensively in some of the other lectures and also in the textbook. But I'll just, in the context of this lecture, I'll just say that magnetic reconnection, and this is from Frank Toffoloto's 2011 lecture, magnetic reconnection is the process where plasma E cross B drifts across a magnetic separatrix, which is basically a surface that separates regions containing topologically different magnetic field lines. So that, just to explain that in words, when you're talking about the Earth's magnetosphere, for example, topologically different magnetic field lines happen often at the magnetopause on the day side because you have the Earth's dipole, which has sort of a magnetic field that's directed up relative to the ecliptic plane towards the North Pole. And that's what this arrow was indicating here. And then during some conditions, you'll have the solar wind magnetic field, which is directed down relative to the ecliptic plane or towards the south or south pole. And so you have these oppositely directed, when you have these oppositely directed magnetic fields, you have a lot more reconnection and a lot more plasma crossing that boundary and then potentially entering the magnetosphere. And so that sets up a cycling of plasma. And then again, you can have reconnection on the night side. This is another case where you can have a separatrix where you have magnetic field lines oppositely directed in the Earth's what we call plasma sheet. And then you have reconnection happening there as well. And this cartoon or schematic, again, pulled from Van Bagenal lecture, kind of gives you an idea of what this does. So in the context of this lecture, all I'm really telling you is that reconnection is a process where plasma can cross into the magnetosphere, across the magnetopause. And why that's important, why I need to go into that is because it sets up a circulation, at least at the Earth's magnetosphere, that's very important. And it causes changes in magnetic field topology that are also very important. So when you look at cartoons like this, and you see this kind of disc-like feature, the plasma sheet, reconnection changes this quite frequently. It changes this topology and makes it from when there's a big reconnection process happening, like you might hear about a substorm, for example, in the context of Earth's magnetosphere, this topology will change to become more dipolar. And what's happening also is that plasma is circulating. So this is like a side view of the Earth's magnetosphere. So you're looking at it, this would be like the North and the South Pole. And plasma is crossing, because of reconnection, can cross into the magnetosphere over the poles and then come down into the plasma sheet. And then through another reconnection process, be basically funneled back towards the Earth, and then circulate back and eventually maybe swept back into the solar wind flow. So there's a cycle known as the Dungy cycle that's very important at Earth. And this basically, we're usually assuming that the plasma entering the magnetosphere is equal to the plasma leaving the magnetosphere via this cycle. And Why it's important though is that it sets up this bulk motion or circulation of plasma that starts to dictate what kinds of plasma flow patterns you have in the magnetosphere, and also where plasma is going to exit the magnetosphere versus where plasma is going to stay inside the magnetosphere and drift on closed paths. So let me go into the next slide. So basically, and again, in the context of this lecture, there's large-scale circulation that's really important in basically all magnetospheres. And it happens from several processes. At Earth, magnetic reconnection is a crucial process. It causes circulation in a large part of the magnetosphere that basically starts to set apart different regions, different regimes of plasma. You have the so-called magnetosheath, you have the plasma sheet, night side and day side, and you have the plasma sphere. And these are all kind of set up by how strong this circulation is, this reconnection related circulation. At other planets, you won't have this feature being quite as important, but it may still be there during some conditions and for some magnetospheres. And so at Earth, you'll often hear this referred to as convection, this type of circulation from reconnection. And you'll also hear associated with that a large-scale convection electric field, which you can think of, it's not convection in the traditional fluid sense, it's just, again, this large-scale circulation of plasma having to do with reconnection. And a convection electric field, you can think about it as being basically and this is pulled right from the textbook from Kibelson and Russell. If you're interested in figuring out exactly how these drift paths form, I suggest looking there, but it's basically you have a large-scale electric field pointing dawn to dusk, and the plasma will tend to drift sunward in the plasma sheet and in this equatorial plane until it reaches some point where it might be swept back into the solar wind flow. So you have the cycle, and you also have this feature inside here, which I'll talk about next, which is related to co-rotation. So all you have to remember about the last slide is that there is this large-scale circulation in the Earth's magnetosphere that's important, having to do with reconnection. But at other planets, that's not as important. And so, but you can do the same exercise. You can look at how strong is the reconnection at other planets, and how does it relate to other types of circulation happening at those planets. And so at other planets, co-rotation is very important. And so co-rotation is basically plasma that's rotating with the planet itself. And it's basically, you have down in the atmosphere, or the ionosphere, the ionized portion of the upper atmosphere, you'll have collisions, and that's going to try to enforce the plasma to co-rotate with the planet. And in many magnetospheres, that they're going to be co-rotation dominated. So you'll see that if you make measurements, for example, of the plasma motion at lower energies, you'll find that it basically is more or less moving with the planet. And so a big difference, and this is again from Prime Bagnall, a big difference between the Earth's magnetosphere and other magnetospheres is that the Earth is not a rapid rotator, whereas Jupiter and Saturn are very rapidly rotating. And that will basically, if you look at the balance between the co-rotation at Jupiter and Saturn and the convection electric field, you find that if you were to draw the drift patterns like I showed on this slide, where you see this plasma going like this, you don't see those at all. You see cold plasma will tend to just co-rotate with the planet much more. And so these are equations that, and apologies, there's a lot of terminology on this slide, but I'll just briefly say the plasma sphere is a region of cold, dense plasma that's sort of where the plasma is co-rotating. At least that's what we call it at Earth. And you can basically look at where the outer boundary of that cold, dense plasma that's co-rotating is relative to the magnetopause location, which we already talked about. And you can write down an expression, and you can see in this expression that one of the factors in here is the rotation rate of the planet. And so at other planets, this boundary, this plasma pause, is like basically a huge fraction of the magnetopause, or it's beyond the magnetopause essentially, which means that you're basically in a co-rotation dominated regime. And so let me see if I have one more slide on this. Yeah, so this is a nice comparison between Earth, Jupiter, and Saturn. And you can see right away that the typical location for where your co-rotation dominated at Earth is a smaller fraction, a fairly small fraction of the magnetopause, whereas 6.7 to the radius of the planet, which if you remember for Earth, the magnetopause is usually at 10 RE. So it's a variable number, but it's not usually out to the magnetopause. At Jupiter and Saturn, it's much larger. It's again out to the magnetopause. So basically, the main takeaway from this is that there's a balance between co-rotation and convection and other large-scale circulation processes. Jupiter and Saturn are rapid rotators, so they're dominated by co-rotation, whereas the Earth is not as rapidly rotating, and some other planetary magnetospheres or moon magnetospheres are not as rapidly rotating and aren't as rotation dominated. So you can have these other drifts coming into play. One other thing I want to say about the slide, and I see there's a lot going on in the chat, so I'll check that in a second, but one other thing I want to say about this slide, I'm not covering, what you're seeing here basically are these lines are more or less what cold plasma is going to drift with. But there's a whole range of other dynamics related to higher energy plasma. At Earth's magnetosphere, when I say high energy, I mean sort of keV and above, tens of keV. We talked about regions like the ring current and radiation belts, for example. They're not going to follow these drift patterns necessarily. They're going to follow slightly different drift patterns, and they're not going to be caring as much about things like the co-rotation and whatnot. And so I'll touch on that briefly later on, but I think because those things aren't as important to the global structure of planetary magnetospheres, I'll probably just see if there's any questions about them at the end and maybe shoot you some references to look at them in more detail. But bottom line, there's large-scale circulation, and it can be driven by a couple of different processes. At Earth, you care about the convection electric field and co-rotation, depending on where you are, and at Saturn and Jupiter, it's all co-rotation. And so let me check the chat real quick, see if there's any.
Mike, I can monitor the chat and interrupt if there's a good question, so feel free to move on.
Okay. Sounds good, we'll do. Let's keep going then. Oh yeah, and I did want to say these bullet points here. So I'm definitely not an expert on Jupiter or Saturn at all, or many of the other planetary magnetospheres. So there are I'll just mention real quick, there are unique processes that happen at those planets because they're co-rotation dominated that simply don't happen on Earth. And so Fran Bagenal's lectures have some good examples of that. And also I think Nick Achilleos' lectures as well. I'll talk a little bit about them when I talk about Jupiter's aurora, but just be aware of that for now, I guess. There's just not enough time to go over all of that. But bottom line, there's large-scale circulation, and the global structure of many magnetospheres is co-rotation dominated, whereas other magnetospheres, there are other processes like convection electric fields from reconnection that are important. So I know you're going to hear about the ionosphere tomorrow from Anthea Koster, so I'm not going to go into detail, but I did need to at least talk about it a little bit because it does have a big impact on the structure of planetary magnetospheres. So first off, what is the ionosphere? It's the ionized portion of an upper atmosphere, and at Earth, there are these different layers that we refer to, the D, the E, the F layer, that have to do with where there are peaks in electron density. And the processes that affect the ionosphere, are things like photoionization. So on the Earth, on the day side, you have a lot more dense, you have a lot more plasma being photoionized. So the thickness and the density of these layers is much more than on the night side. And you can translate that to conductance. If you can think about basically processes in the magnetosphere like large-scale current systems, a lot of them are going to close in the ionosphere. You can think about them maybe using a circuit analogy. So you'll have a current that comes down into the ionosphere and then closes through some path in the ionosphere and comes back out into the magnetosphere. And so when you have these changes, for example, the day-night asymmetry in the ionosphere at Earth, that affects the global structure of the magnetosphere because of the currents that are closing in the ionosphere. So we care about the ionosphere. One example of a large-scale effect on the global structure of magnetospheres from the ionosphere has to do again with that effect of ionospheric conductance. So the larger the conductance, the lower the convection rate at Earth, for example. And these are various models. This is from Frank Toffolo's 2011 lecture. These are various models and observations of the convection rate. You can parameterize the convection rate, or how fast that plasma is circulating that I showed in that figure earlier. You can parameterize it with a cross pore cap potential that's actually measured with ground-based radars, for example, at the Earth. So you measure like the potential drop across the pore cap, and you can measure that and see how it varies with background ionospheric conductance here. So basically what this is telling you is that all things equal, when you increase the conductance of the ionosphere, you decrease the cross-pore gap potential and you decrease the convection rate. So already that's going to change, if I just really quickly scroll back, that's going to change the balance between, where this boundary is basically. It's going to move this boundary out. So so this is one way that the ionosphere can affect the large scale structure. It'll change that convection rate. It'll change the convection electric field. Let me find you a couple more examples that how the ionosphere is important to the global structure. I mean, a huge area of research right now at the Earth's magnetosphere is trying to understand how the magnetosphere and ionosphere react to each other self-consistently. For example, when you have energy deposition from the magnetosphere, this is a cartoon showing you basically electromagnetic energy and particle or kinetic energy flux coming down a field line, and it'll hit the ionosphere. It'll cause Joule heating. The electromagnetic energy will cause Joule heating in the ionosphere. You'll have aurora, but also you're going to deposit. There's a whole different range of kinetic energy or particles coming down, and some of these particles are going to substantially change the ionosphere conductance. So when you change the conductance, that in turn will feed back out into the magnetosphere, like we just saw, and change things like where the currents are closing. It'll change the cross-pore gap potential. And so there's this feedback here that is still a very active area of research. But the long story short is that the ionosphere can definitely affect the magnetosphere in very many ways. And I did want to mention briefly that the aurora, since most of this slide is on the Earth, as far as diagnosing the global structure of the magnetosphere, the aurora are very important. So the aurora are basically the emissions you see when various particle populations come down the field line. And at Earth, you can actually use these are images. I should mention these are images of the North and the South Pole, where you're seeing one particular emission related to one particular type of aurora, and you get this auroral oval, and you get that at other planets as well. And at Earth, the size of the auroral oval is a really great diagnostic of what's going on with the magnetosphere solar wind interaction. If you have a very big or very small auroral oval, it tells you how strong is the interaction with the solar wind. At other planets, it's also the aurora is also a very nice diagnostic of what's going on in the magnetosphere, but you're learning more about different things. At Jupiter, you're learning about processes that are more related to planetary rotation. And at Earth, at Saturn, you might learn about other things, some of which are like Earth and some of which are not. And I'm just going to go to the next slide to give you one nice image of Jupiter's aurora. And so immediately you'll see a huge difference with the Earth, which is that you have these dots. And these dots are aurora associated with Jupiter's moons. And I think this is a really beautiful example of the variety of structure and dynamics that can happen at different planetary magnetospheres. Because at Earth, our moon at Earth doesn't really do anything. It doesn't affect the aurora at all. I mean, it's not even inside the magnetosphere most of the time. Whereas at Jupiter, you have these moons that are basically putting out various sources of different charged particles, and the various processes are occurring at these planets that eventually get reflected in the aurora. And just by remote sensing the aurora, you can tell a lot about what's happening. There's other processes that I'm definitely not an expert on, and I actually think it's still an open area of research what's going on in the polar cap aurora at Jupiter. But the short summary is that people are using these features as diagnostics of Jupiter's magnetosphere, just like they do at Earth. Okay, and so this is a catch-all slide again, because I don't have a lot of time. I did want to, there's a whole slew of different terms, and so you've seen some of these terms popping up on these slides for different regions of the magnetosphere, and there's just not enough time to introduce all of them, but I did want to give you one slide that starts to talk about when you have all these different processes balancing, the convection, the co-rotation, the pressure balance and the bow shock, you set up all these different regions, and you're going to see very different background plasma properties in these different regions because of the differences in the processes that are happening. So just as a whirlwind tour, you have, for example, the plasma sheet we talked a little bit about, where the densities can get a little higher than relative to like the lobes, and much hotter as well. And you have, for example, the magnetosheath, which I'll mention really quickly, which is this transition from the bow shock, the shock that gets set up upstream of the solar wind, upstream of the magnetopause and the magnetosphere. So basically in the magnetosheath, you have a very dense plasma that's kind of compressed and where the flow is being diverted around the magnetosphere. So there's a whole range of different regions we're not going to talk about. The plasma sphere I mentioned is co-rotation dominated. The ring current is the higher energy plasma that's not necessarily following the E-cross-B drifts I showed earlier, where you have that convection and co-rotation electric field balancing. And then you have also the radiation belts. So if you're interested in some of these other regions, there's again previous lectures, and also there's some great references in the textbook to look at the details. But the last thing I'll say about this is that this cartoon will change depending on which magnetosphere you're talking about, because all those processes that control the global structure will change. So this will look very different at Uranus, for example, or Jupiter. Okay, so in my last few minutes here, I wanted to talk a little bit about some of the other things that really affect the structure of magnetospheres. So dynamics can affect the global structure of magnetospheres. The system is never static. We have waves of all types that carry energy, mass, momentum across boundaries and throughout the system. And one type I just wanted to briefly mention is magnetopause surface waves. So you have surface waves in when you have a Kelvin-Helmholtz unstable boundary, which means there's a big flow shear. And so you'll get these basically seed perturbations that grow these waves to a very large amplitude. And so, it's not going to affect the equilibrium magnetopause location directly, because if you average out over time, the equilibrium magnetopause will be reflected in like an average of the boundary location. But these processes are important for the global structure, because this is one process, at least at Earth, where you can have mass, momentum, and energy crossing the boundary that's not related to reconnection and not related to co-rotation. So this is has been called many things at Earth, the viscous interaction, and there's more recent terms as well. But it's another thing that can potentially affect mass, momentum, and energy transport, and by way of that, reflect the global structure of the magnetosphere. And it also happens at other planets. This is a schematic for Saturn's magnetosphere, so you definitely get this process happening at other planets. And then one other example of dynamics, I mentioned way back on that slide that there was a range of values for the magnetopause location. And part of the reason for that, is that the solar wind dendritic pressure is not static. It changes with time. And it's, there are periods when it's higher or lower, and there's also periods where it's dynamic, where it changes very rapidly. And this is another way you can get basically ripples, for example, on the magnetopause, which can set up various dynamics in the magnetosphere, field-aligned currents. And in some cases, again, usually these are going to average out, but in some cases they don't. And a good example at Earth is when you have a very large dynamic pressure change that causes the boundary to move very far in, and that can empty out the radiation belts. Basically, the high energy trapped radiation will get lost into the solar wind, and that sits around. You see that response many days later. So it's not always the case that these dynamics aren't important for the structure. Okay, in the last few minutes here, I wanted to spend a few slides on asymmetries. So I mentioned earlier, and there were some great comments earlier about how there are asymmetries in magnetic fields that affect the dynamics or the global structure of magnetospheres. So when you have asymmetries like that, it can affect magnetosphere coupling, reconnection rates, pressure balance, dynamics. And I think I'll just quickly pause and just see if there's any examples of anyone can think of asymmetries that you've seen in the material I presented so far, or other examples you can think of just in your own research. So any other thoughts on possible asymmetries in other magnetospheres or in magnetospheres in general? Okay, well, people can.
There's one.
Pulsar magnetospheres. Okay, people can keep thinking and putting them in the chat. That's a good example. Pulsar magnetospheres. So yeah, there are definitely asymmetries from pulsars. I'll just quickly show you one, because I think people actually already mentioned this early on in the lecture. There are very tilted and oblique magnetospheres, and so there's a couple of related asymmetries that are shown on this slide, and all of them are important. So I have to go over them really quickly in each one by one. So obliquity, or the angle between the rotation axis and the ecliptic plane, is important, because as we know, co-rotation is important. So where that rotation axis is relative to where the solar wind tends to strike the magnetosphere is important. There are a variety of tilts and angles. The angle between the dipole axis and the rotation angle axis, the angle between the dipole axis and the ecliptic can matter for many of the processes I talked about. And then someone mentioned earlier the higher order moments in the magnetic field. So the dipole isn't always a good approximation, and you can see like at Uranus and Neptune, the dipole is shifted way off from the center. And so you have all these different varieties of rotation axis orientations and magnetic field geometries, and they all affect the pressure balance, the magnetosphere coupling, and the overall magnetosphere structure. At Earth, just one example, these are pictures of the aurora taken from the ground at either end of a magnetic field line. And because of some of these asymmetries in the dipole and other asymmetries related to, for example, the seasons, so one important asymmetry happens because Earth's rotation axis is tilted. You have asymmetries in photoionization rates during the seasons, and you have asymmetries in the ionosphere from the north and the south hemisphere. So there's a whole slew of different asymmetries that come into play when you have this tilted rotation axis, and also the offset dipole. And so you get, basically, long story short, the aurora are almost never symmetric in the Earth's magnetosphere. If you have pictures of, at least in the smaller scales, you see features that are very different. For example, in this case, between the northern hemisphere in Iceland and the southern hemisphere in Showa Station. And then this is the oddball magnetospheres that I didn't really spend much time on, but I wanted to have at least one slide on them. Uranus and Neptune have all kinds of asymmetries that, based on the limited observations we have, of, for example, pictures taken of the aurora from telescopes and the flybys we did with the different satellite missions, they're just way different in structure in terms of the magnetic field topology and so on. So it's something that I'm not going to have time to talk about in detail, but I did want to mention it and say it's a very active area of research.
A quick question in the chat, if you have a quick answer. How are the outer planets, the ice giants, gas giants, magnetic fields generated?
Yeah, that's a good question. And I don't think I have a good answer because I'm not an expert on that, but I know they have that metallic. Well, I'm not even going to say it because I don't know enough about dynamos to answer that. But there are lectures actually, I think, on this topic in past summer schools. I think there was a summer school that talked about the internal structure or what sets up the dynamo.
Yep, similar to the solar dynamo, there are planetary dynamos, and you can have the internal motion and energy from rotation and convection generating currents. And this self-generating dynamo process can happen throughout the universe. But
yeah, great answer. Yeah, and yeah, of course, I think it's a very active area of research, like why you get this huge variety of dynamos. And Mark is exactly right. There's a whole range of different phenomena. The composition of the core is going to be different between the gas giants, of course, and Earth, for example, or Mercury. And yeah, so it's a great question, but there's not a detailed answer, but I think that's the short answer. And this is my last slide. I just wanted to show one example of an east-west asymmetry because I showed this already. And it's yet another example of why co-rotation dominated magnetospheres are different. It's another difference you can get between co-rotation dominated magnetospheres and magnetospheres that aren't as co-rotation dominated like Earth. And you can see here that there's this asymmetry in the Saturn magnetosphere in terms of where you get the larger surface waves from the Kelvin-Helmholtz instability. And that's because the Kelvin-Helmholtz instability depends in part on the flow shear, the difference between the flows on either side of the boundary. And because the plasma that's co-rotating is moving so fast relative to the solar wind flow, it's moving in an appreciable fraction of the solar wind flow, but in the opposite direction. You get more KH unstable menopause at dawn than dusk at Saturn. And you do get dawn-dusk asymmetries at Earth as well, but it's not because of this. The co-rotation rate at Earth is much smaller than the solar wind flow. So another difference, another type of asymmetry that's unique to different magnetospheres. And that's basically it. This is kind of was a whirlwind tour of the different factors that control the structure of magnetospheres. There's the ambient medium, the solar wind, or if you're in a magnetosphere like one of the moons of Jupiter, the Jupiter's magnetosphere. There's the magnetic field properties. like, is it offset dipole? Is it quadrupolar? Or is it stronger or weaker? The rotation rate and the obliquity, the atmosphere or ionosphere, and various asymmetries that we talked about at the end there. So it's really, there's an interplay between all these different factors, you know, convection and versus co-rotation at Earth, or just co-rotation at other planets, or the asymmetries. And you really have to consider all of them when you start looking at the huge variety of dynamics and structure that we've seen in other magnetospheres. So it's a very open area of research, but I think that you can get a lot of the basics of the planetary magnetosphere structure just by looking at simple things like pressure balance and some of the basic processes that are happening at the different planets. So I think I'll stop there and see if anyone has any questions, and just thank you for your time.
Fantastic. Thank you very much. And as almost everyone here has some type of physics training, as part of that training is you're thinking about momentum and continuity and energy. And so thinking about all the potential terms that could be important for your problem. And for a lot of these problems, you can't ignore a lot of the terms, so it becomes very complicated. But go ahead and raise your hand. I see Angelo already has his hand up. Go ahead and ask away.
Hello. Thank you for the presentation. My question was about the two reconnections that take place during the due to the interaction of the solar wind with the Earth's magnetosphere. Yes. The polarity of the magnetic fields that come from the solar wind plays a role whether the reconnection will happen or not, right? Because
Yes.
I suppose they should have the correct polarity as well.
Yes, you're absolutely right. And there's a big difference. So reconnection is practically always happening somewhere on this boundary, but you're absolutely right. It depends where it's going to happen, and how strong it is depends on the orientation of the solar wind's magnetic field. And you have big differences in terms of when the solar wind's magnetic field is more or less oppositely directed to the Earth's dipole magnetic field versus when it's aligned with the Earth's dipole magnetic field. So yeah, it absolutely matters. And some of the strongest activity we get is when they're oppositely directed on the day side, like right here, when we during so-called southward magnetic field, or in this diagram, downward pointing magnetic field. Great question.
Okay, thank you.
Any other questions? Yeah, go ahead.
Yeah, thank you for your nice talk. I have one question, like when a CME interacts with Earth's magnetosphere, then what are the changes that are observed in the magnetosphere?
Yeah, that's a great question. There's a lot of things happening during a CME. It's a very interesting dynamic process. You have different, so the CME has its own internal structure, and the two big things that affect the dynamics are the polarity that we just heard about, the polarity of the magnetic field. Well, actually three things: the polarity of the magnetic field, the strength of the magnetic field, because CMEs often have, one thing I glossed over was that the strength of this reconnection, or the amount of plasma crossing the boundary, depends on not only the direction, but also how intense the magnetic field is. So during a CME, you get a very intense magnetic field. And the other piece is the pressure change, the dynamic pressure change that happens during the CME. So there's a shock front associated with the CME, and you get this. So one thing you often see is the magnetopause boundary, when you have this big increase in the dynamic pressure, will move in. And it also will move in because reconnection is kicking off. So but one thing you can think of, if you think about those two processes separately, just having the pressure increase, you'll have the boundary moving in, and you'll have basically ripples on the boundary as you're kind of accommodating this increased dynamic pressure. So the boundary will move in with the CME, and then depending on the type of CME and where you are in the CME structure, you'll have the CME magnetic field will change and start kicking off reconnection when it moves oppositely directed to the Earth's magnetic field. So you'll see, in terms of the restructuring of the magnetosphere, you'll see the magnetosphere will become much more compressed, and often you'll see plasma moving a lot faster in the magnetosphere. And there'll be all kinds of other processes happening that I didn't have time to talk about, like the radiation belts will often dramatically change their structure. The ring current will intensify. You'll have hotter plasma present in the magnetosphere. So it's a really complex process, but a lot of it again has to do with just that pressure balance and that reconnection rate. Those are the two things that kick everything off.
And one of the reasons why fast CME drive some of the biggest storms is because the duration or the size scale of a CME, it could take 10, 20 hours for it to pass over. So if you think of a north and south turning of a magnetic cloud or flux rope, you can have 10, 12, 15 hours of southward strong field driver. So you're just constantly driving that reconnection. Yep, Mohammed?
Hi, thanks for the great talk. I'm not specialized in magnetospheric physics, but I was wondering if it's possible to isolate the contribution of different sources of magnetic field in the planet. So as far as I understand, there is internal magnetic field produced from the dynamo, and there is one from the plasma system around the planet, and from the crust, and like different sources. So is it possible to isolate these different sources?
Yeah, it's a great question. I'll mention real quick the part of the question I can maybe answer is that you can definitely separate the contribution from the external, the plasma sources. Like when you look at a picture like this, this is sort of what the magnetic field that you would actually measure, if you were a satellite. And there are models, like for example, some of you might have heard of the Suganenko models, empirical models that just take measurements of the magnetic field and they can see that it looks kind of like this. And so you can definitely separate out pretty nicely the external contributions of the field from the solar wind dynamics, from the internal pieces that are more static and they aren't changing, moment to moment as the solar wind changes. But the models of, like, for example, the Earth's magnetic field, we often use the IGRF model to represent it. And I am definitely not an expert on that. So I know that there are ways definitely to separate out like crustal magnetic fields from the magnetic fields coming from the dynamo. And they definitely have ways of separating the different order moments and figuring out how strong each of the moments are. And I think the IGRF is fairly accurate. And there's other models of the internal magnetic field as well, of Earth, for example. So I think you can do it, but I'm not an expert and I don't know like how well you can do it either. I don't know if anyone else, if Mark or Christina have any thoughts on that or.
Yeah, the two big models right now, IGRF, the International Geomagnetic Reference Field, I think it's on its 13th generation. They update it pretty much every 5 years, though the last few years they've had to update it quicker than 5 years because the Earth's field is changing faster than it has in the past. But they attempt to define the core dynamic magnetic field, and then the lithospheric field, because there are asymmetries or iron ore deposits in the lithosphere that have perturbations to that field. And then you have the ionospheric and magnetospheric contributions that change. And so they attempt to separate those out. So you have a good geomagnetic field that you can use for compassing.
Absolutely, yeah. And there are even local like magnetic anomalies, like just near the surface, that there's a whole field of geophysical exploration to figure out, where are there different, magnetic anomalies that relate to like a deposit of a certain mineral or something like that. So you can do all kinds of stuff.
Yeah, they just demonstrated 13-meter accuracy using high resolution geomagnetic fields from an airplane. So you don't need GPS, you just need a really good map of all of these weird asymmetries. But it takes a lot of processing and there's a lot of other noise. Go ahead, Nick.
Thanks very much.
Oh, well, I just wanted to add that so the IG, I don't remember what the acronym is, but the IGFF, is that that's just for the surface field of the Earth, is that right?
It extends up to essentially MEO orbit, though the observations are not as dense. It's primarily right now the main contributors are all of the geomagnetics ground observatories, which have a big northern hemispheric bias, and so they use
Right.
SWARM, which is in polar orbit, to do most of it. So most of the data comes from a few 100-kilometer altitude, but other satellites that have good absolute field measurements are included.
So then Singanyenko is more of a it's a global observational model, is that?
Siganenko actually uses highly elliptical spacecraft. Just the latest version, which is now a few years old, finally included geosynchronous orbit, but essentially
Okay.
before that, it was everything outside of it. And it's just take every NASA, ESA, JAXA
Right. So
satellite and just start doing binning. And
Here's-
the newer ones take the Chapman-Ferraro ring current field line, they represent those and then fit the current strengths to the field. So there's sort of a physics-based model attached to that.
Singanyenko is more, it encompasses more of the magnetosphere.
That's right. It's a magnetospheric model, so it's not good for MEO Leo.
Right, and then those are the empirical models, and then you've got the physics-based, the ab initio models. So, and that's a whole different summer school.
And you combine, oftentimes we combine IGRF and Suganenko together, so you get the blend of both of them. I just real quick, I wanted to mention, I saw Ivan had a question. I can answer really quickly about the aurora. The short answer, Ivan, the question is, are the aurora happening close to the equator because the magnetic field is not co-aligned with the rotation axis? Or is it just a strong storm? I don't know, but I can say that this paper probably has the answer, but I'm just going to speculate, that it's almost certainly due to at least in part, to the magnetic dipole not being co-aligned with the rotation axis. I think that's why you have, because I don't think this feature is rare. I mean, I think it's often that there's very strange, unintuitive locations of the aurora at Uranus. So that's the short answer.
Oh, thank you.
And I don't, is there, oh, go ahead.
Anwisha has a question.
Yes, thanks for the very nice talk. I was just wondering, we have talked that, okay, we need negative BZ from CMEs to create geomagnetic storms, but if there is a positive BZ, but with very high speed and density, it's going to change the magnetopause standoff distance and change things in the magnetosphere. So can it still have some minor consequences on minor space weather consequences on the satellites inside the magnetosphere or something?
Yes, yeah, that's a great question. And yeah, there tends to be a lot of focus on the southward BZ condition, because that's when you have a lot of reconnection happening at the what we call the subsolar point, the day side near the ecliptic plane. But yeah, when you have northward IMF and a high speed solar wind, you can definitely have other dynamics that are important. There are some very important space weather phenomena that happen during northward IMF, and there are unique unique circulation patterns that happen during northward IMF as well. And I think I've seen a couple of papers actually that have looked at more energy deposition to the ionosphere when you have northward IMF in what we call the cusp, for example. So yeah, absolutely. There's a whole slew of different processes that happen during the case where that's not in this like canonical picture here that are very important. So that's a great question. Yeah, there's just going to be different types of phenomena that aren't necessarily the ones that we think of when we think of the classical Dungy cycle.
Great, thank you very much.
Great. So we're at our break time, and I'm going to hand it off to Nick and Christina.
Oh, right, because you got to go. Thank you.
I gotta go.
Right.
Surprise.
Why don't we do a 10-minute break, which I see 11:03. So if you're be back in 10 minutes, so 11:13 for those who are at the top of the hour, 33 after the hour for those at the bottom of the hour. And then we'll go into Mike's second lecture. Excuse me, I've been doing that all week.
Mike, yes. Oh, there we go. Okay, so great first lecture. So now you're going to tell us basically the instrumentation that you need to measure all this stuff, right? Okay, so I'm going to monitor the chat. I'll answer questions as needed. If there's a good question to jump in, I will break in and ask you. Otherwise, we can address them at the end.
Sounds good. Great. So I'll share
Okay.
my screen. Let's see. Get my other lecture up here. Okay, great. Let me put this full screen and swap. Okay, yeah. So yeah,
That's
like
good.
Christina just said, I'll be talking about a whole slew of different instruments now, although actually really only two, and then using them as examples. But this will be more on the instrument side. And so my goal right now is to give you a broad overview of space plasma instrumentation used to measure plasma in fields, which is a really broad remit. And so it's not going to be a comprehensive overview because each of the instruments that we use could be easily a full lecture or more. So instead, I'm going to give a couple examples and focus on common concepts like data levels and noise and et cetera. So yeah, just to start off, just to get a sense, how many of you would consider yourselves modelers and theorists who only kind of use data to validate your model? Okay. Great. Okay, so a fair number of modelers. So I'll definitely try to make this talk understandable, so at least you get the broad strokes of things to be aware of with data. Now, what about people who are observers, who mostly work with data? Okay, got a fair number of observers. Very nice. So then, okay, so then some people might want to keep their hand up, but who of the observers, who would actually like to build instruments or be an instrument PI? Basically lead an instrument team. So we still got hands up. Okay. Sounds good. So some people are like, probably like, no, I don't want to build an instrument, but I'll just use the data, which is fine. Okay, great. So we have some future PIs, future instrument designers, which is great. So I'm going to try to gear this talk to all all the different groups here. And yeah, definitely. I see Dan says I'm on the fence about that. Yeah. I definitely. It's one of those things that once you get your feet wet with data, you'll kind of get the sense of whether you want to delve into the world of building instruments or not. And I'll have some thoughts on that. I actually consider myself an observer. I've definitely worked on instrument teams and so on, but I've never actually really been in a lab with like an oscilloscope, doing the hardware stuff. So there's definitely something for everyone in this area. So, but hopefully you'll get something on whether you're a model or an observer or a future PI, you'll get something out of this. So because this is such a broad topic, I'm just going to basically throw up these references right at the beginning, just so you're aware of some much more in-depth references for your particular instrument or area of interest. So there's an excellent set of AGU monographs called Measurement Techniques in Space Plasmas for Fields and for Particles. These are each books with like, really dense chapters on each instrument you might be interested in, sometimes more than one chapter on one instrument. There's also a really nice scientific report from the ISI on calibration of particle instruments in space physics, which doesn't just talk about calibration, but also introduces some of the particle instruments. And so these are good for like broad strokes overview. And then also there's numerous instrument papers for specific missions. And I'm going to draw heavily from some instrument papers from the Themis mission today, and I'll put some references to that at the end. But when in doubt, especially for more recent missions, you can probably find an instrument paper if you're interested in a particular data product. So with that, just go to this broad overview of, just to give you an idea of the many different missions that are out there. And actually, this doesn't even show a lot of the missions that some of you might be working on if you're looking at the outer planets, for example. But it just gives you an idea. And the reason I put this up is because you can immediately see, you know, first of all these satellites look different. They have different, you know, some of them are spinning, some of them have solar panels, some of them have shields to block from the sun. And some of them are sampling the solar wind, some of them are sampling really close to the sun, some of them are sampling in the magnetosphere, some of them are orbiting other planets like Mars. And so the reason I put this up is to basically make 2 points. One is that we have instruments operating in very different environments, from like the upper atmosphere ionosphere to the magnetosphere to other planets to the sun to the solar wind. And so you're going to have to customize for the different areas you're in, and you're also going to have different mission objectives. So some missions are focused on, you know, something related to the sun or the solar physics. Some are focused on the near space environment and so on. And so, you know, when you start to look at the vast range of instruments that are out there and all the ways that they're customized, it all comes back to this, like the fact that each of these missions has their own objectives and their own area they're operating in. And they're all going to be, you know, operating under those constraints, basically. So you're going to see a vast range of different customization. And this slide kind of gives a little more about that, what I was just mentioning. So like I said, there's numerous satellite missions out there with very different scientific goals, and they're operating in very different environments. And just by way of introducing the very different environments, I mean, this is from that West et al. ISSE report, but also from the cluster ESA missions proposal way back. And it just shows you the range in energy and flux, or number of particles coming in these different regions of the magnetosphere and the near the Earth, and also in the solar wind. And you can see right away there's, you know, there's very narrow distributions related to the solar wind because of the bulk flow in the solar wind. There's more of a broad distribution across many energies in the magnetosheath. There's much lower fluxes in the lobe. And so if you want to build a particle detector to study the solar wind or the lobe, for example, you're going to make it very different. If you're looking at the lobe, you're going to have to detect really small numbers of particles. And so you're going to have to really account for that in your particle detector. It has to be really sensitive. In the solar wind, you might not have that issue, but you might have the issue that you're only looking at a very narrow range of energies. And so you start to design instruments around these. And, you know, if you're someone who's like a modeler, for example, and you're looking at a particular satellite measurement, and you're like, why is it, you know, measuring something that's completely different than what I thought? It might be because it's in a region that the detector wasn't designed to operate in. And so that's one of the things to think about when you're looking at different instruments. They're designed for different purposes. And so the instrumentation is driven by the scientific goals of each mission. And so someone who's studying the solar wind near the Earth might not care about the radiation belts of the Earth, so they might not build a detector to look at those kind of particles. And there's always trade-offs. And this is something that gets lost, I think, in a lot of the discussion of when you're just reading an instrument paper, or you're just looking at data that you get from NASA on CEDAW, for example. But there's always trade-offs when you're building an instrument. There's power. How much power are you going to get from your satellite? The telemetry, how much data can you send back? What's the weight? How heavy is it? What's your weight budget for the satellite? How much does it cost? So you don't have an unlimited budget. You never have an unlimited budget. And these are all drivers for the choice of instruments. And so sometimes you might want to build a really fancy particle detector that can measure a vast range of particles, but you only have the money and the power to build one that can measure solar wind, for example. And some instruments work better in different environments, you know, high versus low beta plasma. So you'll have some, you know, if you're flying a mission to the Earth's ionosphere, you might use one technique to measure an electric field, whereas if you're flying into the you know, outer magnetosphere, you might use a different technique to measure the electric field. And so that's why you get this vast range of instruments used to measure in plasma and fields. And so that's why there's no way I could possibly cover all of them today, but I'll just give you some high level things that relate to two instruments that kind of are common to all instruments that you might look at. This is more of a slide just for the future PIs, and it's really the only slide I'll talk about this for. But I wanted to, well, first of all, I'll give a plug. If anyone does want to become a future PI, I've actually never attended this workshop, but NASA runs a workshop that's come highly recommended to me. And if you're someone who wants to build a mission, be on a mission in the future or be a PI, check out the NASA PI Launchpad workshop. And this slide was from Sabrina Feldman from some of their online materials. But the reason I'm bringing this up now is again, getting back to this point that really NASA and other space agencies force you to think very carefully about what you're designing your instrument to do. And you always need to trace down from your science question goals to the actual instrument that you're building. And this is kind of the process. You start by asking a question, and then you hone that question into a detailed hypothesis, and you kind of get some sense of what measurements you need to test the hypothesis. And get very specific too, like what's the frequency range you need to study for a particular wave, or what's the number of particles you expect to need to observe for this particular phenomena. And then you trace down into like the actual instrument that you need to make that measurement. And so this is really crucial if you ever want to build instruments. And it's not something that modelers and theorists won't necessarily have to think about too much, but except when you're looking at data that you're grabbing to validate your model, and you're like, why is this thing again not working like I thought, or why is it measuring something that's completely different? I guess my bottom line for modelers and theorists is that you shouldn't by default trust the data, because the data might be wrong. It might not be designed to measure the environment you're looking at. And I'll get into that in a little bit later. But this is kind of that balance that that you have to think about when you're looking at any kind of data collected in space plasmas. Okay, so I'm going to just introduce two instruments in depth, in some kind of depth, actually not in that much depth, but I want to use them as examples to talk about other instruments and common issues with them. So I'm going to start by looking at magnetic field instruments. And one of the reasons I chose magnetic field instruments is because magnetic fields are really a vital parameter for understanding space plasmas. They're actually flown in a lot of missions. Various types of magnetometers are often flown, regardless of what environment you're looking at, whether it's a solar wind near the sun or other planets. And they help you understand the plasma. You can characterize whether the plasma is strongly or weakly magnetized to get the beta parameter. If you have a particle detector, you can understand charged particle motions, determine plasma wave properties, all kinds of useful things to diagnose the plasma. And so I'll introduce a few techniques again to measure magnetic fields, but also use them as an example to highlight issues that are common with other instruments. So tools to measure magnetic fields, so magnetometers. So magnetometers are just instruments to measure magnetic fields. But when someone says they're using a magnetometer, you have to ask them what type of magnetometer, because there's this huge slew of different instruments that you can see here on this chart. Definitely don't feel like you have to remember all of these. It's just to give you an example of how much you can customize things depending on what phenomena you're interested in and what regime you're interested in. So the reason you have such a vast range of magnetometers here, different types of sensors, is because not all of these are necessarily used for space weather or space plasma diagnostics. Some of them are used on the Earth's surface to study, like we were heard in the last lecture, the Earth's internal magnetic field. Some are used to study like the near Earth, the lithosphere. Some are used to study actually for defense applications, like you try to detect if there's a submarine or something, because that's a magnetic anomaly. So there's a whole field of magnetic anomaly detection that people are interested in. So you get all these different sensors that are looking at really faint signals, really strong signals, high frequency signals, low frequency signals, operating in space environment or on the ground or in the air and aircraft. And so that's why you get this big range of variety for magnetometers. But it turns out that there's really only two. I guess more and more there's going to be three, but there's really only two that are, I would say, widely used in space plasmas, and that's the flux gate magnetometer and the search coil magnetometer, which is also unfortunately called the induction magnetometer. So it's a bit confusing. You might have heard both of those terms thrown around for that. So I'll focus on these two. There's also new sensors being used called magneto-inductive sensors I'm not going to get into, but the bottom line again is there's just a huge variety of different sensors. And even with the flux gate and the search coil, those are customizable themselves. But one thing they have in common, and I think that sets them apart from other instruments you often see in flown on spacecraft, is they're usually small. They usually don't take a lot of power, and they're relatively accurate. What I mean by that is, like, for a magnetic field measurement, you often speak about knowing the magnetic field to a small percentage, or even a fraction of a percentage. Whereas with a particle detector, you might be happy with a factor of 2 or 5 even, or something like that. So they're relatively accurate compared to other sensors usually. So basics of a flux gate magnetometer. Again, I would say you don't feel like you have to remember this because there's many different types of magnetometers, but I just wanted to give you the flavor of what things you might do to measure magnetic fields, and just again give an example of how you can customize things. So for a flux gate magnetometer, you're operating with the principle of having two coils wrapped around a ferromagnetic material, the drive coil and the sense coil. And so you drive in the drive coil with a sinusoidal current, and then you measure what happens in the sense coil. And it turns out that the coil will reach saturation every half cycle, and the properties of that saturation will have to depend on the properties of the material you're putting in there and how much current and whatnot. But the reason this works so well to measure magnetic fields is that if there's no ambient magnetic field, you get a particular signal or odd harmonics in the sense coil. Whereas if there is an ambient magnetic field, you get even harmonics, and the voltage that you measure associated with those harmonics is proportional to the ambient magnetic field. So it's kind of an indirect way of measuring magnetic fields by looking at the properties that you measure in that sense coil with a known current that you're driving with. So again, the basic principle here is that you drive with a certain current, and then you have it wrapped around a ferromagnetic material, and then you measure, and the thing that you measure depends on whether there's an ambient magnetic field or not, and the intensity of the magnetic field. So basically that's the principle, and you can put a bunch of these, in different axes and measure the three-dimensional magnetic field. So it works really well for getting vector magnetic fields. This is actually, I believe, from a magnetometer that was put on the surface of the moon, but you have magnetometers that are more compact than this that are put on satellites all the time, more flux gate magnetometers. And they're used again in spacecraft on the ground and high and low temperature and so on. So they're really versatile. So this one is another type of magnetometer that's I would say much easier to understand where they're coming from with this, because it comes from your basic E&M textbook. Basically, it's basically just a solenoid, although there's a vast range of physics contained in that and design considerations contained in that. But basically, a search coil or an induction magnetometer just works on the principle of magnetic induction. You have a coil of wire, and any time varying magnetic field will make a voltage that you can measure, an EMF. And the voltage that you measure will have to do with the properties of the coil, the number of turns of wire, how many turns of wire there are, the material inside the core. And so the big difference between this technique and the flux gate is that the induction magnetometer, because it's measuring time variations in magnetic field, does not give you the background magnetic field or the baseline magnetic field. So it's not good, would not be good for measuring something like the Earth's internal magnetic field or the internal magnetic field of other properties. Basically, any static magnetic field, this will not work for. But it works really well, and it's very customizable. The coil is wrapped around, it can be wrapped around just air, or a lot of times people will wrap it around some kind of magnetic core, which will boost the sensitivity, allow you to measure weaker signals. And it's really hard to describe how vast the range of customization there is for search coil magnetometers. You can tune things, and there are labs that actually have a whole setup just to do this, to like tune the number of turns of wire, the core material, how long this thing is. They also put on these neat little things at the end called diabolos, or flux concentrators, that basically boost the amount of signal you can get, or magnetic flux inside the sensor. And so as you're tuning all these things, you and there's a really couple of references by Koyo and others that talk about how you can model this thing to basically tune to the phenomena that you're interested in. So if you know something, if you know like the range of frequencies you're interested in, and you know their typical amplitudes, you can design this thing and tune these different things, like the number of turns of coil, how long it is, how thick it is with the material and all that, until you can measure the thing that you want to measure. But again, the principle is very simple, and you can write just a simple circuit diagram to see that. And again, there's a whole range, and I'll direct you to this reference and other references, a whole range of different customization that's not captured in this really simple expression. But at the end of the day, it just comes down to you're making a measurement of a magnetic field, and it's just based on Faraday's law. You can measure a voltage based on the time varying magnetic field when you know something about the properties of this coil. Okay, so that's just two examples of how you measure magnetic fields. The two most common instruments that have flown thus far in situ and in satellites are flux gates and search coils. But let's talk about some common issues for all instruments that can be where magnetometers can be used as an example. So noise is one issue, and noise can mean many different things to many different people. And there's a variety of noise sources that in particular affect magnetometers that are often frequency dependent. And so one type of noise that is often talked about is the noise inherent to the instrument. And you can characterize that very well by laboratory tests or by modeling. And in fact, that Coyle and Leroy paper I put on the last slide talks about that for a search coil, how you model it. But basically, you can put the magnetometer in a lab and in an unmagnetized environment, and you can just see what signals it measures as a function of frequency. It shouldn't measure anything because there's no magnetic field, but it does measure something because there's just an inherent lowest amplitude signal you can measure with a sensor. And like I said, it's frequency dependent. This is the noise spectrum for the Themis flux gate magnetometer. It peaks at lower frequencies and then it drops off. So this is something you can measure and model fairly accurately. And the same thing is going to be true for other sensors too, like electric field instruments and so on. But there's also noise, other types of noise. There's noise from the electronics on board the spacecraft and from magnetic fields from the spacecraft itself. And so these are something that a lot of times you try to model as best you can in advance of launching, but you often discover there are sources of noise you didn't consider, and you just have to correct for that after the satellite launches. But this is why, so magnetometers are really a nice instrument. They're very popular, but one thing that makes them unpopular for satellite missions is that once you put a magnetometer on, you often have to think about magnetic cleanliness, which means you have to have the other instruments accommodate the magnetometer, basically make sure they don't turn on and off at the wrong time, or they're not putting out lots of artificial magnetic signals that contaminate the measurement that you want to make. But the bottom line, I think, from all of this is that noise characterization is very important for any instrument. And the weaker the signal of interest, the more important it is to know the noise spectrum of the instrument. So let's say you're a modeler and your model is really pushing the limits of like discovering a new plasma wave or something that has a very small amplitude. If it has a very small amplitude, then like relative to all the other waves that have come before, you really have, when you start to validate your model with an instrument, you really have to consider that and think, okay, I need to talk to these people about, is the thing that I'm measuring actually noise, or is it the wave that I'm interested in, for example? So that's one example. Another example, which I couldn't find like a rigorous definition of data levels, but I did want to introduce that concept of data levels because it's very important when you're grabbing data from any mission on like NASA's website or other websites. It's not just NASA, other space agencies use data levels too. And basically the basics of a data level is that you start, there's a data processing pipeline for any of the measurements you want to work with. So the thing that you start with on the satellite, for example, with a magnetometer, is just a voltage. Like if you look at the search coil magnetometer, you're just going to have a voltage coming out of that thing, and then it's going to have some arbitrary timestamp that's related to like the clock that's on board the spacecraft. So that's completely useless to you if you want to study space plasmas. You have to do some processing to advance that data to a higher level. We would call, for example, level 1 for magnetic field data, where you're not showing a voltage. Now you're showing nanotesla or nanotesla per second, depending on whether you're looking at a flux gate or a search coil. And it's actually a timestamp that you can work with, like an UTC or some other time that you're familiar with. So this data processing pipeline goes from level 0 to level 1 to something you can work with, but then it might still not be quite polished. It might not be the final data product. Usually the final data product you want to work with is level 2. And as another example for a magnetometer, your level 1 data might be, for example, in some weird coordinate system that's if you're in a spinning satellite, it might be in the spinning frame of the satellite. So that's not really useful to you because you want to know like what the magnetic field is relative to like where the Earth is or where the sun is, for example. So then you'll advance it to level 2, where you have actually calibrated magnetic field measurements in units of nanotesla and some geocentric inertial frame like GSE coordinates, GSM coordinates, or something like that. So this is just the concept of data levels. I couldn't find a rigorous definition from level 0, level 1, and level 2, and I think it really varies from mission to mission. I put another example up here. You don't have to read this, but it's for an Earth science mission at NASA, and other missions will have their own definitions, specific definitions of data products. But the bottom line thing you have to remember is just that there's a data processing pipeline involved before you can work with the data, and you have to think about that pipeline sometimes. And I'll get to that on the next slide when you're actually looking at the data and figuring out what's going on. Unless you're someone who's designing instruments, you'll probably never work with level 0 data, but you still have to think about this pipeline when you look at some issues that can come up with the higher level data. I put a question on this slide, but maybe I'll just pause here and just ask if anyone just kind of reading this example can think of any other examples of level 1 data for other instruments you've worked with, or just pause and see if anyone has any questions. So yeah, if you want, feel free to throw any examples of level 1 data, and I can give a couple more if people are interested too. Counts, yeah, that's a good one. That's a good one. Yeah, counts. You'll have it for particle detectors. You might have counts in some like detector frame, like counts in this or that direction in the spacecraft frame, and then to go to level 2, you need to do some other, coordinate transform or figure out where the counts are coming from and pitch angle, for example. So like bring in the magnetic field measurement and then get a pitch angle distribution. So that's a great example. Yeah, counts is great. IV curve, yep, another great example. Then you'll get to density after that, for example. Okay, great. So yeah, we could, I think you'll see some examples of this too in the activity, the lab activity for electric fields. And there's just a lot of different things that happen in this pipeline. Okay, great. Yeah, another one, uncalibrated X-ray UV images that have traces of particles. Yep, you're going to clean those to get to level 2 potentially. Yep. So let's get to this. So the reason I introduced data levels and the reason I think you're dealing with it in your activity is because again, if you're a modeler, you're probably never going to care about this stuff, except for the fact that it's going to introduce problems with the level 2 data sometimes, and you have to do some detective work if you want to use the data to figure out what those problems are and where they're coming from. So, for example, for magnetometers, there are some things that can happen when you go from level 0 to level 1 to level 2 that can introduce unwanted signals into the level 2 data. They can come from many sources. One example is the fact that sometimes you need to bring in attitude information from the spacecraft, and that to get to like the magnetic field and geocentric inertial coordinate, geocentric inertial frame, for example. And sometimes you don't have that attitude information, or sometimes it's corrupted. So this is an example of when that happened for the Themis magnetometer, and there's a paper about this topic, and I'll just walk you through this example really quickly to see what's going on here. So when you transform magnetic or electric field instruments, if you're on a spinning satellite, this only applies to a spinning satellite, but when you're transferring them from the spinning frame to a geocentric inertial frame or to a coordinate system you want to work with, like GSM or GSC, you need to have the attitude information. And for example, to get that information, you'll often use a sun sensor. So what I mean by attitude information, by the way, is you're spinning around and around, and you need to know, need to have some fixed reference for where your spin phases, or like where your fluxing magnetometer boom is pointing at any given time. So for example, one fixed point of reference is the sun's location. So if you have a sun sensor, when you're spinning, okay, I just passed the sun, coming back and just past the sun. And so that works really well for getting that attitude information to despin or to move to another coordinate system you want to work with. But when the satellite goes behind the shadow of the Earth and enters the eclipse, now that doesn't work anymore. You can't see where the sun is because you're in the shadow of the Earth. So then you start getting errors in attitude information in that where you are in the spin period that start accumulating. And you see this really nice waveform if you look at level 2 data that just comes from CDOWEB during one of these eclipse periods. And this is basically all garbage because it's basically you've lost track of where the sun is, and you don't know what you're doing basically for the despinning. And you can model it though. If you know what's going on here, you can model it and you can get the actual true magnetic field with this black curve here. And so the reason I'm bringing this up, so if you're someone who doesn't work with data a lot and you see something strange like this, and it's really important to your work, it's always good to contact the instrument team and figure out what's going on. But even if you don't do that, sometimes just reading the instrument paper or going to the instrument website, you can learn about these things and see examples of them, like in this paper. And there are ways you can avoid it. If you want to do like statistical analysis, for example, you can just throw out the periods when the satellite is in the eclipse of the Earth, because they don't happen very often. But this is just an example, though, of something to be aware of. This data processing pipeline isn't always perfect. So never trust the data, at least not when you see something strange like this, is the short answer. So yeah, so let me just quickly summarize the magnetic field instruments. They're really versatile, use them for a wide range of mission objectives. They're used throughout the heliosphere. They come in many types and subtypes. They're highly customizable. but they are affected by common issues that also other instruments are affected by: noise and unwanted signals from data processing. So some ways you can deal with this, depending on how deeply you want to dive, just read the metadata, try to read the instrument paper, and talk to the instrument team. And sometimes it's not even a big amount of work. Sometimes you can just read, if you go to like the instrument website, they'll often have common issues that you can just read about, and then you can know, okay, when the probe is in the eclipse, I just need to throw out those data, and it's a super easy solution. So those are some ways to deal with this if you're more on the observer or modeler side. Let's see. Okay, and I did want to say that I have no time to go over it, but I wanted to mention electric field instruments, and I know they're part of your activity too. And so it's a whole slew of different, another parameter that's really important for space plasmas. And just briefly, the three techniques that often are used to measure electric fields are double probes, or closely related Langmuir probes, if you want to measure just one, with some approximations, one component of the electric field. Electron drift instruments, which rely on E-cross-speed drifts of emitted electrons to get the electric field normal to be, and particle detectors, because you can measure velocity moments, and you can use those to infer electric field normal to magnetic field under some assumptions, so it doesn't always work. But for low frequencies especially, it might work. Yeah, and like magnetic field instruments, the electric field instruments are also affected by noise and unwanted signals. And I think you're learning about this one in your activity, that there are, for example, electrostatic wakes that are an unwanted signal that electric field instruments can often pick up. And so that's something to be aware of when you're looking at level 2 electric field data, for example. And again, they can be tailored to the region or region of interest, basically. So I think I'm doing okay on time. I'm not 100% sure. I think I have at least 15 minutes left, which should be enough for this bit. Is that right, Christina? Or?
Yeah, you're good, Mike.
Okay, thanks. So I'll spend some time then talking about electrostatic analyzers, because I wanted to give one example of a particle instrument and use them as an example for other instruments as well. So one of the reasons I picked electrostatic analyzers is that they're widely used throughout the heliosphere to measure particle distributions, and they can be customized to different regions. You use them to measure particle flux at different energies. You can calculate moments such as velocity and density. So they're really, really useful. And I'll just introduce a couple of techniques that you can use to measure charged particles with ESAs. And again, highlight some examples of common issues with other instruments. And this is a picture of the Themis satellite electrostatic analyzer, which was flown on one of these was flown on each of the 5 Themis satellites. So this is a really basic introduction to ESAs and how they work. Basically, all they are is they perform a differential selection in particle energy. And the way it works is you apply an electric field or a potential difference between 2 curved plates, and that will guide the flight path of the particle. So there's an energy-dependent drift path or radius that gives you a differentiation in energy. So you have particles entering here, and the radius of their drift path will be different depending on the energy they're coming in with. And also you see in this equation that there is a dependence on charge. So automatically, when you design an ESA, you're designing it for, or you're only going to measure ions or electrons, basically, depending on how you design them and how you apply this electric field. So it's one way of automatically separating charged particles out. There's really nice material in the West et al. 2007 report, if you want to read more details on this, and also that monograph I mentioned earlier. But basically, one thing that this diagram doesn't show you, so you have particles entering here, and depending on their energy, they might end up at different locations at the end of this drift path. And then you need to count them somehow. And so that's something that also varies from ESA to ESA. In the Themis ESA, there's a microchannel plate that's used to get the number of counts, but other ESAs might use a different technique. So this is a really, really simple introduction to them, but there's lots of customization. And so one thing you'll probably start to scratch your head about as you look at this diagram, and everyone kind of does, is what happens when the particle doesn't come in like straight on like this? What happens when it comes in at an angle? And so the ESA instrument designers have thought about this, and they've addressed this in different ways. Sometimes they don't want it to pick up the electrons coming in at an angle, but there's ways you can address this. So cylindrical ESAs are kind of the simplest one that doesn't address this. They basically they're more they're less complicated, but they're more difficult to measure the full 3D distribution function due to the narrow acceptance here. But you can do it with a spinning spacecraft or with multiple cylindrical ESAs. But more common is to use some other geometries. You'll sometimes see spherical ESAs, quadrispheric or hemispheric, and it basically, instead of doing a cylinder, you have two spherical surfaces. You still have a potential difference between the two surfaces, but you have kind of something more like great circle paths, and then that lets you sample 2D particle distributions. And then you have top hat ESAs, which are another kind of refinement to both of these designs, where you'll have another section kind of before this section that will basically be deflection plates that kind of help guide the particles into the area where they start to become differentiated. And that lets you scan a wider range of angles. So that's kind of a whirlwind tour to the different geometries. And there's a vast range of different geometries that have been used, you know, all kinds of combinations of this, all kinds of techniques for counting up the particles. And all of it again comes down to what plasma regime are you looking at, and what how much is your budget? Can you make a huge ESA, or do you have to make a small ESA? How much space are they giving you on the spacecraft? So you know, a lot of times we have these constraints where when people are designing ESAs, they can't build, you know, something that can measure everything because of they don't have unlimited space, they don't have a limited budget. Okay, so that's again a whirlwind tour of ESAs. I wanted to give you some examples of common issues with ESAs, and one of them you can probably already guess. So ESAs, like other instruments, are only designed to cover a certain range of energies, angles, and frequencies. So I'll just pause here for a second and just ask this question. The fact that you're only measuring this range of energies, angles, and frequencies, how do you think this might impact moments of the particle distribution, things like density and velocity? So anyone have any thoughts on how the fact that you only measure a certain range of angles and frequencies might impact the particle distribution? And it can be, there's more than one answer for sure. Yep, so Sky says only see one population at a time. Definitely, that's a good example. Also depends on your field of view, yep. Yes, limited angle may not allow it to detect particle beams, very important. And I'm not going to show it, but there's great examples with the Themis ESA, which was not designed originally to measure the beam in the solar wind, but it can be modified to do that. But if it's not pointing the right way or in the right mode, it'll miss the solar wind beam, the bulk flow of the solar wind, which will throw off your measurements significantly. Yep, Nick, go ahead.
I just, you mentioned something really quickly, and maybe I missed it earlier. I just thought it was worth reviewing how you are, sorry, oh, okay, I'm not sure what, but Zoom was trying to tell me something. I'm not sure what it was trying to tell me. Anyway, I'm not sure if you mentioned how you get density, so what you're measuring and then how you get density from that. So from measuring the spectrum, getting density and velocity from that.
Yes, yeah, so yeah, I should have probably put a slide on that, how to get the moments from the particle distribution. Probably easiest just to explain with density. The density moment is just simply integrating over the distribution. So you basically have counts at different velocities or different energies with one of these particle detectors, and then you just add up all those different counts across all the energies, and that gives you the number of particles. So that gives you the total number of particles, and then to get a density, you basically have to yeah, actually that's a good question. So you have to know something about the volume of space that you're measuring it to, which is another feature that's actually kind of not, I wish I had put a slide on this for this. But yeah, you're integrating across you have basically the distribution function as particles as a function of energy or velocity. And when you add up across all of them and divide by the volume, you get you get the number of particles as a function of velocity, which you can convert to the density. But I don't think I can explain this very well without an equation. I don't know if anyone has Maybe what I'll do is I'll defer this until I can pull up an actual equation that shows you it, unless one of the other people want, like Christina or Nick, if you want to chime in and show something or say something that's a more succinct summary.
It might be a good introduction to the lab because they'll be looking at some of that specifically. So maybe we can, over the break, we can try and find something.
Yes, definitely. Yeah, it's not, I should have thought about that. It's not intuitive. Yeah, I mean, you're basically getting the number of counts. You can have flux or differential flux, and depending on how you're counting the things up, and then basically there's an integral over the distribution function as a function of velocity, for example, to give you that you can get a density from. But yeah, it's not intuitive as I'm saying it in words, so I think I need to show an equation to do that. But what you're seeing here, though, back to this example, here, this goes back to, I think, the example that Sky was saying about only seeing one population at a time. The ESA detector on Themis was not designed to measure all energies. It was only designed to measure a certain range of energies. And it turns out that the lower end of their energy range does not extend down into the range that typically is covered by the plasmasphere, that cold, dense, co-rotating plasma I mentioned in the last lecture. So what happens is you have other techniques on the Themis spacecraft. For example, you can infer density from spacecraft potential, and that works pretty well in the plasmasphere. And you see that that's what this green line is showing you here. And you can see it's much larger than the densities measured from the ESA electron and ion moment. And so what happens is you'll see later on in this example interval, the two numbers get closer to each other and eventually they match. And that's because what happened was basically there was some dynamics in the solar wind, and it pushed those plasmasphere particles, it accelerated them a little bit such that they had a high enough energy to be detected by the ESA. So that's when you start to pick up more density, and then it goes away because you don't have that flow anymore. So by the way, again, I should mention this for those who aren't aware, or haven't looked at this type of figure before. This is basically a spectrogram, in this case, an energy flux spectrogram. And the color basically indicates the number of particles as a function of energy on the y-axis and time on the x-axis. And people who look at this a lot, you can tell pretty quickly like what region you're in, based on, for example, in the Earth's magnetosphere, the typical energies in the magnetosphere are like maybe 10 keV, 1 to 10 keV. And so, okay, now I know I'm in the magnetosphere. And then this population here, when it shoots down to like 1 keV or lower, now I know I'm in the Earth's magnetosheath, for example. So it's not intuitive when you first start looking at this, but that's basically you can kind of use this type of plot to figure out what's going on. And so when I look at these little green patches that just pop out of nowhere at the bottom of the figure, that's just from what I've seen before, that's because these particles are being pushed so that they can be detected by the ESA, and then they go away whenever energy from the solar wind is gone. And so later on in this interval, when the probe leaves the plasmasphere around here this time, and is in a region where the ESA is detecting the full or almost the full distribution function, then the densities all line up really nicely. So this is just one example of how you can basically miss the distribution. In this case, the ESA from Themis just wasn't designed to detect a plasmaspheric population. So that's why you're missing it here. And that's basically just what I said.
So Mike, there's a quick question about the black line on the electron panel. I'm not sure exactly which black line. Oh, down at the bottom, there you go. The question is, what is that?
Yes, so another thing that affects ESAs is the spacecraft potential. And that will determine basically what particles you can detect, and maybe sometimes will make you not detect the particles. So it's a reference point. And you can see right here, there's the black curve underneath it, there's this population. And it's meant to, I think the reason they show this on this plot is meant to show that we shouldn't trust necessarily the stuff happening below the spacecraft potential, but I'd have to double check that. But I believe that this black curve is the spacecraft potential for Themis. So it's converted to an energy. So depending on the voltage of the spacecraft, these low energy particles may or may not be deflected or affected by that. So it basically affects what you can detect with an ESA. And there are other, when you look at these kinds of plots, there are other curves that you'll often see on them, or other lines. So In this case, I think it's spacecraft potential, but there can be other plots like this where they might put other charts, or sorry, other lines. It depends what feature you're trying to look at. Yeah, great question though. I'm pretty sure it's spacecraft potential in this case. And I should mention actually the one before I go on with that, I'm not going to have time to talk about it, but since you mentioned it, spacecraft potential is very important. It's like extremely important, especially for some regions like the Earth's magnetosphere. If the spacecraft is charged positive or negative relative to the ambient plasma, it can definitely throw off some of your measurements especially for low energy particles. So when you look at other missions that have flown at Earth, like HOPE or just other missions in general, Van Allen probes, which flew the HOPE detector for cold plasma, for example, spacecraft potential control is very important. So there are satellites that actually try to control the spacecraft potential so that they can measure the things that they want to measure and not the things that they don't want to measure. So it's actually a great whole separate discussion we could have about that at some point if maybe if there's time at the end. But a very great question and great comments. So this is one last example I wanted to show of unwanted signals from the environment using ESAs as an example. So ESAs can pick up many undesired signals, including penetrating radiation. And what I mean by that, real quick, is that this detector, is basically meant to have, sort of a certain range of energy particles coming in and being deflected. But high energy particles, like in the Earth's radiation belt, don't really care what this detector is doing. They might be coming in at all different angles. And when you have higher energy particles coming in, there are techniques that people use in ESAs to get rid of them or account for them. But what they do is basically they can create secondary electrons when they hit the detector that can get picked up by, for example, for Themis, the microchannel plate. They can also create X-rays or Bremsstrahlung that can also be picked up by the microchannel plate that you're using to detect counts. So basically, when you have these kind of secondary electrons and like Bremsstrahlung creating artificial counts, can you think of any ways that might, just a question, can you think of any ways that you having this extra unwanted signal might affect your distribution function? And I definitely, as you're thinking, I'll definitely put up the equation for the distribution function so you can, I think that'll be a little more clear when I show that, what exactly, how this might affect things. But yeah, maybe while people are thinking, I'll just give this one example. Yep. Murdy says it artificially increases signal at different energies. Definitely. Yep, that's exactly right. You'll get these spurious counts, and this is what you're seeing actually in this example from the Themis mission again. So what you're seeing here, it's another energy flux spectrogram, and in this case, the energy range goes higher because they're including another detector, the solid state detector at Themis, which can measure 10 to the 5th EV or 100 keV up to even MeV electrons and ions, electrons and ions. And so you see, when you look at this layer period, there's this population of hot ions and hot electrons that pops up, going up to even 100 keV. And as soon as that happens, you see this green area in the lower energy ion distribution or energy flux. So down at like 100 EV or 1000 EV, all the way down to even 10 EV. And that kind of peaks right here when you have the hotter electrons peaking up here. But then as you go forward in time, it lingers. And you also get, as you see, it also lingers here. And it doesn't really go away until the end here when you lose the hot electron population. So basically what's happening here is these hot electrons are creating unwanted counts that you're picking up with the Themis ion detector. And it's creating this artificially large density. And they've modeled it in this chart to show you what the actual ion density should have looked like. It should be basically around this black curve. And then basically you have this artificial population that doesn't go away until the very end. And so this is another example of how you can, when you're looking at a density moment or a velocity moment, there are some pretty wacky things that can happen that have to do with, picking up these other populations. And with the Themis mission in particular, like I've seen a lot of examples where when it enters the Earth's radiation belts, there's all kinds of alarm bells that go off because you have to really look carefully at cleaning up this kind of contamination. Because the Themis mission, although it was designed to operate in the radiation belts, they knew going into it that there would be things like this happening. And the same thing is true for other missions, like MMS. MMS doesn't even usually sample with a lot of its instruments in the radiation belts because it wasn't designed to do that. So some of the instruments actually don't even turn on when it goes through that region. So just be aware that this is another common issue that can happen with other detectors as well, that you can get these unwanted signals from the environment. And so to summarize, ESAs are really versatile. You can use them for a wide range of mission objectives that come in many types and subtypes. There's affected by just the detector range that you're designing for, the population that you're designing for. You might not be able to detect things outside of that range, and also unwanted signals from the environment. And the solutions are still the same. Read the metadata, read the instrument paper or the website, and if you're ever unsure, talk to the instrument team. And then, so again, this is my catch-all slide, I guess my last slide, that because I can't go into them, I don't have time to go into them, but there's a slew of other instruments used to detect particles. And each of these that I have on this list here, there's often subtypes and other types that aren't reflected in this list. And sometimes there's mixtures of instruments or overlap, but you'll often see things discussed like Langmuir probes, retarding potential analyzers, magnetic spectrographs or spectrometers, energetic neutral atom imagers, which is actually a remote sensing technique, Faraday cups, solid state detectors, and plasma wave instruments of various types, which you can use to infer density from characteristic frequencies. So there's a whole range of other things to explore if you're interested in measuring particles, and depending on the environment you're looking at, one or more of these might be useful. So that was basically the summary, or that was my talk basically. Again, it's just looking at two instruments as examples, and covering some topics that are covered common to all instruments. So just be aware, as you're looking at data, that data levels or data processing pipeline, noise, instrument range of performance, and unwanted signals can all affect what you're trying to do with the measurements. And I'll put the further reading slide up one more time at the end after this slide. So you can, if you want to do a deeper dive into one of the other instruments I mentioned, you'll be able to do that. And just final note for future PIs, just remember you have a lot of choices for instruments. And the important thing is to always carefully trace from your science objectives to the measurements to the instrumentation. And then for everyone else, just be aware that there are these different data levels. So one thing that surprised me when I was starting out working with data is that there is a vast range of difference between like level 1 and level 2 data. And there's many different types of level 2 data. And so always knowing what level you're working with, what data product you're working with, and then trying to check the instrument paper if you have any issues is always really useful. Anytime you have some kind of data analysis you're doing, or if you're using something for model validation. So I think that's it. I'll just leave this last slide up with the references and see if there's any questions.
Great, thanks a lot, Mike. I know we are going into our break a little bit, but this is a great introduction to the activities that are coming up later today. So we'll take a couple of minutes for see if there's any quick questions, but we also have sort of a office hours right now. So Mike, if you can hang around for the next hour-ish, people can just unmute themselves and pick your brain about a bunch of different things. Because as you said, there's lots of stuff we aren't able to cover in the short period of time that we have. We'll take a quick question from Andreas.
Yeah, so this is, I guess, kind of related. So this problem with the density for the electrostatic analyzer, is there a similar issue with like Faraday cups when measuring normal plasma density, where you might have these spikes due to like, Bremsstrahlung? Well, I guess if you're measuring protons, you wouldn't expect it maybe, but is this just a common thing for ESAs, or are the other instruments where, for example, you see these problems with density measurements?
I think it's a common issue. It's not just for ESAs. Yeah, and in fact, the ESA, even for ESAs, there are varying degrees of having that issue, depending on what technique you're actually using to do the counts. So in Themis, they're using microchannel plates, but there might be other ways of doing it where you might be more or less affected. And I think Faraday cups, I'm not too familiar with them, but I'm guessing, I'm assuming at some point they need to make counts somehow. And I think if I remember, Faraday cups use different layers of, I'm not going to be able to answer in detail because I'm not familiar with Faraday cups, but I can answer in the simple way, which is that the answer is almost surely yes. Because I think everything that has to make a count usually will have some issue that it'll be affected by some other population. So if it's in a high radiation environment, usually there's some kind of something that can create artificial counts. So I can actually during the office hours, bring up the instrument paper, one of the instrument papers on Faraday cups, though we can look at that, see if there's any more detailed discussion on it. But it's a great question, and I think the short answer is there's going to be some effect, but it might not be as big an effect as like the ESA example I showed from Themis for sure, and it's going to depend on the design of the Faraday cup.
Again, compare.
Great. So yeah, why don't we just move into office hours? I think I'm gonna have to duck out for a second. Nick will be here, and Mike will just hang around. So for those of you that need a break, go take a break, come back. If you want to hang around and pick Mike's brain on various things, just stay here and raise your hand, unmute, and feel free to have a conversation. And then Nick, you wanna, what is it? We're coming back at the top of the hour. Is that the plan?
Let's give it a full hour.
Hour?
And so
Okay.
come back at either 10 after or 40 after, depending on what time zone you're in.
Sounds great.
Sounds great. And just for Andreas, I'm pulling up the Faraday cup. This by the way, I don't know if I have the link to this here, but I probably should have put that in my lecture, but this is one of the references, and it talks a great deal about those kind of unwanted signals and counts for various instruments, including Faraday cups. So maybe we can find the answer really quickly here. It's actually one of the first chapters, 13. And while I'm bringing this up, if anyone else has questions, you're welcome to ask, but let me see if I can refresh myself on how these work. I've actually never used a Faraday cup before, so I don't know if anyone else is on who has used them, wants to chime in. Let's see, page 13. I think it's right up here. Here we go, Faraday cups. So it says there might be issues with escaping secondary electrons. And there should be to measure very low ion currents and additional shielding, there should be use of screen. So I think again, for Andreas, this just short answer is Faraday cups are probably affected by unwanted signals from the environment, but I'm guessing it's a very different way it's affected than compared to, for example, the ESA I mentioned. It looks like there are some issues with secondary electrons, which also does affect ESAs as well, but maybe it's affecting Faraday cups in a different way. And maybe this, if you wanted to get into a deeper dive into it, it sounds like this, some of these references like Gilmore and C, or maybe just even this ISI reference would maybe be helpful for you. So I can, if you don't have this or if you can't find this reference, let me know. I can send it to you or ask Nick and others to send it. And so I get questions about the distribution function. Let me see if I can bring up a reference on the distribution function here. Because I think there's two levels to that question. There's the level, like the textbook, how is the equation for the distribution function, but then there's actually also the level of how is the distribution function computed, like using actual data. And there are approximations that go into that. Let me see if I can bring up a couple of papers that talk about that. Let's see here. So I want to bring up MS. I think this, and I don't know, Nick, if you have a textbook handy.
I don't have the a text handy that would cover this question in particular. I think we might, and this could also be a good, I mean, maybe this is a whiteboard topic for when we come back as a whole, because the first part, they've done the first part of the activity looking at the electric fields last night in their time zone groups, and we will review that. But then the second part of the activity is looking at the spectrograms for ESA and SST and comparing them to the plasma variables, the density and the velocity. So it might be a good introduction to that.
Mm-hmm.
Oh, is this the?
Oh, I'm just, yeah, this is not
Yeah.
gonna, this is, what I'm reading right now is the instrument paper for the Themis ESA and how they actually get the distribution function from the counts, or the number of basically how they get the distribution function from the measurements. But I think even better to start with would be to find a reference, like a textbook reference on the distribution function. And I can probably find one. If I can't find it in my reference, yeah.
Like, and I think both of these questions are valuable because, you know, there's pings on the detector, and then, but from that you've got to get a distribution function, and then it has to do with the what's the energy settings on the detector, and then how do you do that with a spinner?
Yeah, it's challenging. I mean, yeah, we can definitely talk about that. I see, is it Hager has a hand up? I don't know if you want to ask a question while we're chatting here.
Yes, thank you so much for your presentation. Actually the ionospheric response during the geomagnetic disturbance is basically different from the northern and southern hemispheres, such as maybe the auroras is much intense in the northern hemisphere than the southern hemisphere. The plasma densities and irregularities as well. So I'm wondering if the magnetospheric ionospheric coupling can explain that, maybe the magnetospheric convection or something. Just if you have an explanation for that.
Yeah, great question. By the way,
Thank
can you pronounce your name? I'm sorry if I said it wrong. Is it?
Yes, it's right, Hager.
Okay, great, great, Hager.
Thank you.
So yeah, that's a very interesting question. The asymmetries between the North and the South, it's actually an active area of research on the interplay between the asymmetries that are kind of inherent in the system, like the Earth's magnetic field is asymmetric. It has an offset dipole, and it's it's tilted, and there's asymmetries in the ionosphere just because of seasons. So like the northern hemisphere is in summer when the southern hemisphere is in winter, so you have different ionization rates. So there's an interplay between those kind of imposed, or those pre-existing asymmetries that are already there, and then the asymmetries coming externally, like the solar wind can hit the magnetosphere with different disturbances that might be asymmetric between the North and the South. So these things are asymmetric, but then the system itself responds to that and might create its own asymmetries. And I think the short answer to your question is that some of the asymmetries that we observe in like the ionosphere, like the irregularities or differences in precipitation, are maybe coming from both of those types of asymmetries, from stuff that's internal, like the Earth's magnetic field, and stuff that's externally imposed. So there's definitely a balance between those things, and it's an active area of research. I think there are, like I said, there are some asymmetries where like we know for sure what's causing it. We know it's coming, like the fact that the ionosphere is more ionized in the summer hemisphere compared to the winter hemisphere. We know that very well just because of the photoionization rate, because the sunlight is hitting the summer hemisphere more than the winter one. But there are other things, like you said, like scintillation, which may or may not, or not scintillation, irregularities, which may or may not be, it might be related to many different sources of asymmetry. So I don't know if that answers your question, but I'll say is it's an active area of research, and there there's potentially more than one explanation depending on the phenomena that you're interested in.
Thank you so much. Thank you. Also, I have another question. It may be so basic, but you showed us the magnetosphere shape for Earth and Jupiter, and I saw that the magnetosphere shape from Jupiter is different from the Earth. Actually, I think the solar wind flow, which is the main contributor to define the shape of the magnetosphere, especially the compressed one from the sun, but it is different from Jupiter. Is it depends on the distance from the Jupiter to the sun?
Yeah, it depends in part on that. Yeah, it's as you move away from the sun, the solar wind density decreases, and that's part of that pressure term, the dynamic pressure term. So the amount of pressure at any given point on the Saturn's magnetosphere, sorry, on Jupiter's magnetosphere is less than at Earth. There are some differences in the solar wind speed as well, but they're not as dominant in effect as the density. So yeah, the part of the reason why Jupiter's magnetosphere is so big compared to the Earth is in part because the solar wind density is lower out there. But there's other, I would say that's probably not the most important part. I think the fact that Jupiter's magnetic field is so much stronger compared to the Earth is another big reason why it's such a large magnetosphere. But you're absolutely right that the solar wind dynamic pressure changes. It gets lower and lower as you move out in the solar system, and that will create, all things equal, create larger magnetospheres. So yeah, great question.
Yeah, okay, thank you so much. I appreciate it.
And meanwhile, while there's time here, I'm going to look at the distribution function. And I see there's also some more stuff in the chat on that. So I'll try to find an equation, but it looks like people are already answering it, which is great. Thank you for doing that. I need to find a good equation that shows us. Oh yeah, go ahead. Is it Kataki?
Yes, Kataki.
Kataki.
Yeah, hello. So I wanted to ask, like, what changes we have to make in our instrument if we have to make it for like ground-based or like spacecraft like based or space-based instrument. So what changes we have to make in the magnetometer?
Yeah, great question.
What challenges we can face? Yeah.
Yeah, great questions. There are definitely differences between whether you're deploying, for example, a magnetometer in space or on the ground. Sometimes it's not intuitive though. Sometimes it's actually in some ways more challenging to deploy it on the ground compared to in space because it depends on the environment you're operating in. But I would say that some overriding things that you have to consider if you're going to space is the weight. Weight is a big consideration, or mass, I should say. Mass is a big consideration if you're putting something on a rocket. There's always, for any satellite mission, they're always going to give you a budget for the mass, and so you can't put a huge magnetometer on a satellite. So you'll often see that ground-based magnetometers tend to be larger and heavier than the stuff that gets put on a satellite. So that's a driver of the design of the magnetometers is the mass. Another thing that magnetometers in space might have to be aware of, especially the electronics related to the magnetometer, but also the sensors, is the radiation environment. That's something we don't really care about on Earth's surface because we're not bombarded by the high energy radiation that the satellites that are in, like, for example, going through the radiation belts of Earth or Jupiter might experience. So because of that, they have to use potentially more shielding on the electronics and those sorts of considerations that you wouldn't necessarily have to worry about it at Earth on the surface. So those are some of the biggest drivers. There's also another big one is telemetry. So one other thing that we have at many locations on the Earth that we don't have to worry about is data transmission. I mean, we still have to worry about it. If you put a magnetometer in some remote location, you have to somehow get that data back, over Iridium satellite or internet or whatever. But if you're in space, if you're launching a magnetometer to Jupiter or Saturn, you have a very limited capacity to transmit the data back. So you can't collect 1 kilohertz samples all the time and send all of that back. You have to somehow reduce the amount of data you're sending back. And so that's important if you're measuring higher frequency waves, for example, at another planet. So at Earth, we don't have to worry about that. We can, fill up a 10 terabyte hard drive. We can go out and grab it, bring it back, but satellites can't do that. So those are some of the big considerations that come to mind. But I will say, like, as someone who's worked with ground-based magnetometers a lot and has deployed them in places like Antarctica, it's not always easier to deploy stuff in space. Like on the ground, one thing that you have to worry about that sometimes you don't have to worry about in space is the big temperature swings that you might get between like summer and winter. You also don't have to worry as much about corrosion. Like if you're putting a magnetometer near the ocean, on the coastline or something, salt water can be a big damaging thing that can damage electronics in your sensor. So there's other considerations on the ground that will depend on where you're putting your sensor. But yeah, that's a very short answer. I mean, I think the biggest thing again for satellites versus ground: size, mass, telemetry or data transmission, and the environment that you have to design for. Like, is it radiation intense or is it high temperature, and those sorts of things. Great question.
Thank you. Also, we don't have to change any design, like in designing, like the design will be same, just we have to take care of a lot of other parameters that are challenging, like temperature, yeah, as you said, but we don't have to change the design, like the basic structure of the magnetometer, right?
The basic principle of the magnetometer you don't have to change. Like, you can still fly a flux gate magnetometer in space or on the ground. You can fly a search coil magnetometer in space or on the ground, but again, because of the limitations you have on mass and volume sometimes on the satellite, it forces people that, like, let's say, I know there are some groups that design induction magnetometers or search coil magnetometers, and the ones they put on the ground will be big. Like, they'll be like, as big as my hands are across here. Whereas in space, it might be like this big. And that's because they're forced to like figure out a design that can work, that can be small enough to fit on a given satellite. So the basic principle hasn't changed. You're still dealing with a coil of wire, but you're tuning the parameters, you're changing the materials that you're making with the magnetometer with, so you can make it smaller and fit on a satellite and have a lower mass. So that's a short answer. Like, the basic principles don't change, but you will often see that the magnetometers designed for space are shrunk and those sorts of and are wider sometimes as well.
Thank you.
Yep. And Omina, is that right?
Yes, it's correct. In the lecture, you mentioned that when the spacecraft is not able to record the results, it can give us a very good curve in which these curves may not really reflect the actual data itself. And instead, the modelers can be able to filter the actual data from the results. I just wanted to find out what is the technique that the modeler can use to get these results, and what are the parameters these modelers will consider if they want to get these actual results.
Yes, great question. Let me bring this up real quick. Trying to remember. So basically, I think the short answer to this, if you're a modeler trying to get this result, hopefully most of the time you won't have to deal with this kind of feature. Ideally, the instrument team will fix this. Sometimes they'll release something called like a level 3 data product, which is like corrected level 2 data. That's the short answer to your question, is that if you see something strange like that, hopefully they have a technique to fix it. But the longer answer, I think, is that you could do it yourself too. So a lot of these NASA missions will release all of the supporting what they call housekeeping data, basically the engineering data about the satellite, like where is the sun sensor pointing, is the satellite in the shadow of the Earth, or is it outside of the shadow of the Earth? Is there an issue like this happening? And so I think what these authors did in this paper is they figured out that the satellite was in eclipse from that housekeeping data. And then and this is where I don't remember exactly the details, but I think they figured out with a model how the satellite spin rate should change over time, such that even though they didn't know where the sun was located because the sun sensor wasn't working at this time, they still could accurately model like the spin phase of the satellite. And that's what they really needed to get the corrected data. That's the black line here. So that's the longer answer. I don't have the full details in this paper. Is in one of the references at the end, and they would have the full details in that paper on how they did this. But the short answer, if you're a modeler and you just want to use this data, ideally you will never have to deal with this because no one wants to do all this extra work to get you just kind of want to trust the data and use it. So hopefully the instrument team will be able to correct these kinds of things in level 2 or level 3 data?
Okay, Michael.
Yep, great question. Okay, and then I'm going to go back to my search for seeing if I can find a distribution function equation, but I did see some questions in the chat, or some answers from Ivan. Yes, particle energy distributions aren't the same as the distribution function itself. Okay, let me try to search for an equation. I don't know if it's in the, is it, I don't know, Nick, do you know if it's in the textbook? There should be equation. I mean, like in my
I don't think it's in, I don't recall it being you're talking about the Schreiber, the big text, the full text,
yes.
okay.
Yeah, but I mean, it's a basic thing. If worst case scenario, I can pull it up. I can actually show it in my camera because I know it's in the Kivelson and Russell text. Yeah, it's let me see. But the more advanced question about the more advanced question about how the detector does this will be a little bit more involved. I'll have to dig into the instrument paper for that. But it's a good discussion because it's not a simple right.
I'll go pull up. I gotta go find Kivelson and Russell.
Yeah, I mean I just got it right here actually. I was just looking at it. I can actually show you the thing. I mean, they have an assumption. Well, actually, what they're showing in the Kivelson Russell is an assumed distribution, which is actually not what I was hoping for. But it is an assumed bi-Maxwellian distribution, and I think they have a kappa distribution as well to show examples. But really, I mean, this is like an assumed distribution. You probably can't even see it.
Well, you know what I'll do is I'll take a picture of it, and we can. I'll go find my. Yes, I see that. Yeah.
Yeah, I mean, this is an example, but it's never as simple as a Maxwellian.
Sure.
It's usually, but there's a couple examples.
Right. Okay.
And there's an equation too, that maybe this equation will be helpful. It shows you, I mean, basically what it does, I'll just give you the example for the kappa distribution. It doesn't really matter what the distribution is. It's more the, oh, it's probably backwards. That's no good. Is it backwards for you?
No.
Okay, good. Let me just zoom into this.
Well, I can, yeah. I'll go pull up my copy. Which chapter is it in?
It's in chapter 2, section 2.3.
Okay, I'll go pull up my copy. I'll take a picture of it and we can share it on the screen.
Yeah, and in the meantime, I'm going to pull up. I know there's better examples. Even Wikipedia probably has one just to show the equation of how.
I'm a little anxious because what I have them looking at is the spectrograms that are. So is that distribution a slice through a time slice through the spectrogram?
Yes, and
okay.
it's usually energy. One thing you have to be careful with. I mean, it's not gonna. A lot of times they show energy flux versus number flux, and I think if you're using the equation that's in the textbook for getting like a density moment, you probably would work with number flux. It depends. It depends what moment you're looking at too, actually. So.
I see. It's energy flux. Oh, that's bad. Okay.
Well, it'll introduce. I mean, you'll still get an answer that's related to the density, for example, or the velocity. But depending on how you're, I don't know if you're pulling up.
I'm going to take your screen.
Yeah. If you can show how you're pulling up the.
Actually, I'm going to do this. I think we want the whole screen.
By the way, the reason they show energy flux.
Yeah.
It highlights different plasma regions better than if you were showing number flux, because as you like the Earth's magnetosphere, for example, as you go up in energy, the number fluxes decrease, and so the regions like that bright reds, the red that's at the top of the figure on the top, that doesn't pop out as nicely if you show number flux, because the numbers of particles at those higher energies is usually lower. And it gets even worse in the radiation belts as you go to higher energies. So that's
Right.
one of the reasons they don't show number flux. Let me find out. Distribution function, calculate moments. I'm sure I can find a good.
So, and I'm asking mostly qualitative questions about like comparing like what in your discussion about like using both instruments together, right?
Yeah, yeah. Let me share my screen real quick, because this is just a really simple equation I just found that at least is something I can speak to. Again, it's not what the satellite is actually calculating, but it just shows people the simple equation for getting density when you have a distribution function. So basically number of particles in a given location at a given velocity or energy and at a given time. And so you integrate this thing up over all the energies or all the velocity,
right?
And then you get your density. And that's as simple as that for the density. So, but it's not simple when you actually look at not necessarily simple when you start implementing this with a particle detector, but that's probably what I would start with. And I'm sure this equation exists somewhere else. I just need to find it. And I've seen lectures on this too, like on how to get the moments from the particles. I'll try to find one from my grad school classes. I think I might have one, but
I would be impressed
if I can find it. Yeah. Let's see. I'm going to stop sharing for a minute.
Okay.
See if I can get it. But definitely we can show that one, and I'll also, if I can't find the lecture notes, I'll at least show the instrument paper that might talk about it.
Okay.
Oh, the title of the Kivelson and Russell, it's called Introduction to Space Physics. I'll put it in the chat.
I'll put it in chat. You look for what you are, what you're doing.
Okay. Okay.
The title isn't important because they're all like introduction to space physics and introduction to plasma physics, and so but there's the link, and this was so Kivelson and Russell is probably the first significant textbook in the field. So something to keep in mind. It's both both it both is like very complete, but also at this point a little dated.
Yeah, there's definitely some new things that have happened since that was released. I mean, MMS, THEMIS, all these missions have come about.
Right.
Okay, so let me share my screen real quick. And I think I can actually, even though this was from my UCLA notes, I just found a link online. So I think it's shareable because people could just Google that link themselves if they wanted to. But I'll share my screen real quick. There's a good description of moments of the distribution function that's actually talking about it more from the perspective of going from the detector, whatever detector that is, to the actual moment you want. And then it has a nice succinct definition of the density, velocity, and temperature moments. So what I'm going to do is, this is actually from a PDF, but I found this link, which again, let me just give credit. This is to UCLA because, but it's online, so anyone can grab it. So I think it's okay to share, because anyone can grab it. So I'll put this in the chat. Let me just make sure it's the right thing though. Like it actually links to stuff that, yeah, it does. Okay. So that, again, this is going to be a little dated. I'm not sure when this was released, but again, credit to UCLA because this is coming from there. But there's a lot of good description here, and the one particularly on the distribution function that might be of interest is, let me see, is this chapter 6, which doesn't match up with, oh, here it is, chapter 6, deep space instrumentation.
Huh.
Hopefully it'll come up. I don't know how much longer. Oh yeah, go ahead.
Well, the link was broken for me.
Oh, can others get to that link? I don't know if anyone else can try. Maybe it's something like my, I don't think I have anything running on my computer that would allow me to access that others wouldn't be able to. But now I can't access it actually, or I'm not able to go to one of the other links.
I was having this problem last night where a bunch of certificates seem to have aged out. Yeah, chapter 6 is everything after chapter 4 is not, doesn't work.
Okay. Yeah, maybe whatever server I used to, it doesn't exist anymore. Well, at least I can project it maybe if people want to see it, and I mean, eventually I think I could probably talk to like Vasilis or one of the other professors at UCLA to see if we can share them with the summer school. But yeah, they have like nice simple introduction to like a Faraday cup, which is really nice actually, because it's a lot shorter than the that longer reference I was showing earlier, and a couple of the other detectors. But then later on here, they talk about the moments, so we can definitely get into this either before the activity or whenever you want. But yeah, they're.
I think it's a good intro for the activity, because there's some assumptions that I made that I was going to have to explain. So if you can that you explain them is probably better than me explaining them.
Okay, I can try. Let me see again if I can find it though in the best thing of all will be if we can find it in the actual ESA instrument paper for Themis. And there might actually be in here. I can definitely speak to some of the, like some of these kind of charts, for example. Let me see if I can find a good equation.
Oh, so the lecture slides from that on that website are available.
Oh, do you see any anything that covers distribution functions? Because that would be very helpful.
I'm looking though.
Meanwhile, see if this thing has a good intro too. Oh, this is good. Conversion to physical quantities. So this actually would be, let's see if this has a good, because I know this report is definitely publicly available. Anyone can download it. Let's go to the right section here, chapter 5, or page 5. 2. Here we go. Particle fluxes. Yeah, this is a good reference, I think. I can already tell it's gonna introduce like number flux, differential directional number flux, because these even I, like, my head is usually spinning when I look at these different I mean, they all have different uses, but like you were probably showing total energy flux. I think that's what is typically given on CDAL web, unless you specifically ask for yeah, and then you can do directional differential energy flux. So like a subset of that spectrogram from like only when the detector is pointing in a certain direction, for example. So let me, yeah, this is good. This is even better, I think, than the UCLA lecture potentially.
Oh, okay, great.
So I can go through this maybe. I'll put this one in the chat because I think people can easily grab this one. I see report, West calibration. I think this one is freely downloadable. Pretty sure it is. That's weird.
That one worked for me. I was able to download that one.
Oh, good, good. Yeah, let me put the link then. I don't know, for some reason I couldn't, I don't know why it's just showing me an image, but I'll put this in the chat and then hopefully people can grab it. Yeah, I mean, I think the short summary is that there's a lot of ways you can get the distribution function, and each mission might do it differently. And they also have different techniques depending on whether they're doing it on board the spacecraft, like automatically versus on the ground, where they can correct for different things. And so I can definitely introduce some of that stuff, Nick, if you want, before you do your
Sure.
thing. Yeah.
Let's do it in this order. I'll repost the mural board that I was showing you earlier. And we'll take a look at the electric field stuff first, because I think there are some interesting features there. And then I'll have you review the distribution, going from, counts on, so is in this case, the electrostatic analyzer, what they're doing is they're scanning through the energy, right? So they're ramping up the selection voltage to look at to scan through the energy. So I'm asking you, I'm not telling you. They're ramping up the selection voltage, and so for every time step, they get counts for a particular number of particles for a particular energy. Is that?
The way that ESA works, it's probably, I don't think it does a ramp. It just has a constant electric field applied between the detection plates, and the way it gets the energy is by basically filtering. It's because of the radius of curvature of the different drift paths for the electrons or ions is different depending on the energy. So
I see.
So like where they get deposited on the detector tells you what their energy is, basically.
Got it. Okay.
But other detectors do it differently, like what you're talking about. So,
okay.
So yeah.
I think I was that was from when I was trying to do the same thing with like wind. Was trying to understand what wind was doing, but we'll go with this.
Yeah, then there's one other piece I'm just blanking on, but I'm pretty sure that the only thing I think I'm gonna have to think about when I explain this is the tricky thing with that always is a stumbling block when explaining this is the how you get, like, it's kind of easy to explain the distribution function as a function where you get the energy and the time, but the volume is not intuitive because you're measuring a flux, and that's kind of where the volume comes in. but I've
Right.
never really found a good way to explain why you're getting a density as opposed to just the number of particles, how you get a volume out of that. And it's because you're measuring, you're measuring a flux, and I have to think about a good way to explain that.
Well, do you have to have an estimate of the bulk? Do you have to calculate the velocity first?
Yeah, you get the energy, you get the velocity. Yeah, the energy tells you the velocity basically. You're basically getting an estimate of the kinetic energy of the electron for an ESA, depending on where it's deposited. So you know that. So you get the velocity and the energy. You know the mass. You're making an assumption about the mass, which doesn't always work for ESAs. Oh yeah, let's see.
Right. So then my thinking is that you've got some area of a detector, right?
Mm-hmm.
And then if you know what the velocity is for a given time, and I always just think, well, like, in a second, how big is that, right?
Yeah, no, that's great. I think you're right. That's right. That's a good diagram to have. We should leave your cartoon up. That's a great.
Well, I think I can redraw it pretty quickly. So what volume is being swept out by the plasma as it goes past the of course, then you've got to figure out, like, is the plasma moving or is the spacecraft moving? And then that's a whole nother, I mean,
yeah, you're right. There's definitely different regimes where that assumption works. And I'm remembering now too, there's the geometry of the detector that can play a role too. And there's correction. I'm remembering now with like this is not for ESA, but with like the solid state detector on Themis, there are correction factors that you apply to get the density that have to do with the properties of the detector. But I think your basic diagram there is good for this, because I think you can go a lot further with it, and there's other things that are going to depend on what energy you're dealing with and all that stuff. But I think it's a first approximation. That's a good explanation. And this might actually, if I go a little further, I might talk about it.
You should do anything that you need to do in the next 10 minutes or so to or 20 minutes, well, 15 minutes. We're back in about 20 minutes.
Okay. Yeah. I might actually go grab some water and tea or something and come back, and I can bring this up later. Okay.
We can all go to the, thank you, Shelley. We can all go to the Miro board, but I'm going to share it, my view right now. So let's see. Yeah, so I mean, you're all looking at similar sorts of things going on, of course, because I directed you to the same general thing. Oh, we've got a very complete poster from Time Zone Group 5. So just to emphasize, one of the goals of a spinner is a spinning spacecraft. One of the reasons you would have a spinning spacecraft is that you can have one instrument that then is looking in a bunch of different directions, right, over the period of the spin. And so then you better know what the spin period is, so you can deconvolve that over time. That's in contrast to, and I don't know that we emphasize this a lot, but the stereo particle instruments that we were looking at, the data we were looking at yesterday, stereo has a bunch of different windows that it gathers its angular distribution over. And so it doesn't have to spin, or at least not for that instrument anyway. It's not spinning, and I think spinning would be complicated for stereo, because it's also like an imager, right? So if you've got an imager on board, are there any examples? I don't know if Mike or Christina have any examples of a spinning spacecraft that has an imager on board.
Well, it doesn't really count, but Galileo, right, which went to Jupiter, had a spinning part and a non-spinning part, which caused actually all kinds of problems because you need to spin half the spacecraft and still be able to talk between the two pieces. So there was, yeah, kind of craziness that was happening. But that's the one I know about. I don't know, Mike, if you know another version of that. I think they tried that and decided that was maybe not the best idea.
Sometimes doing both things at once isn't a good idea. Yeah, I don't know, but I see some in the chat. I can't think of any actually. Most of the ones I've worked with in the Earth's magnetosphere are spinners, but they don't have imagers. So yeah, I'm not sure the combination.
Yeah, so Ivan mentioned RESI, which is kind of an interesting thing because they actually use the spinning aspect of it to deconvolve their data, right? So they actually built the spinning part into how they image the X-rays. So they've got grids, and then the fact that they spin creates this pattern, which they then used Fourier transforms and all this stuff to kind of deconvolve and recreate an image. So that's kind of actually a innovative use of using the fact that you're on a spinning spacecraft to make images, but that's not usually how it's done. But yeah.
So, so here's what I think is going on in the data you were looking at, and then we can get Mike's input on some of this as well. And I have at least one question for him. So, this looks like a from July of 2007. So we look at the despun data and we see these interesting blips, right, that appear to happen. They're not quite daily, but they appear to happen on a regular basis. And so if you look at the spacecraft orbit, I think this is the top. Yeah, this is the top down. So this is the polar view. It looks like we're going in and out of, we're going through the magnetopause in this case. So am I interpreting those blips appropriately?
Are you asking me, Nick, or?
Yeah, I am asking you, yeah.
Yeah, so most likely those very large blips, when you're seeing like 150, 200, 300, 200 millivolts per meter, that's actually because you're measuring the electric field in the spacecraft frame. And actually, as you move closer to the Earth, there's basically what you're measuring is the geophysical. You can think about it like this: like the measurement you're making contains the geophysical electric field that you're trying to measure from the Earth or from the magnetosphere. But there's another term related to the spacecraft motion, and you can write it down as like this: basically the flow moving past the spacecraft as the spacecraft's moving into the magnetosphere is creating its own electric field. So in the frame of the satellite, you have a term that's like V satellite cross B, more or less. And as you get close to the Earth during perigee, you're moving very fast. And so if you're in the frame of the satellite, that's what will give you, most likely give you those spikes.
I see. So this, you're saying that this here. Okay, I thought I lined it up with the, then I guess I wasn't looking at it carefully.
Well,
so here, yeah.
There can be definitely big electric fields at the magnetopause too. Well, that's for sure. But just looking at the regularity of it, like if those are every 24 hours or every orbital period, it's more likely, or it's plausible that it could be that due to the spacecraft motion, the electric field due to the spacecraft motion.
Okay.
But yeah, we could check closer and see if we can line it up.
Yeah. Okay.
We actually in our group checked it, and those spikes happen when it's very close to the Earth. So. Okay,
great. Thank you.
And by the way, if you're getting these data from CDAW-Web, I don't think that Themis mission releases this, but like other missions like Van Allen probes release the data product for the spacecraft frame and also for the Earth frame. And there you'll see, like, you can compare like the two charts for both of them, and you'll see that spike will go away for the most part for the Earth frame electric field.
Okay, great. Okay, so it's not, I was hoping to interpret something physical out of this, but well, it's physical, but it's not maybe not telling us as much about the magnetosphere as we'd like. I think the other interesting thing is these are the zoomed in versions of one of these spikes. And so you've got down on the bottom here, we've got the spinning portion, so the 1/8 second portion, and then this is the despun portion. I am really curious. I mean, so certainly it looks like we've got these artifacts that you were talking about. So I couldn't get the data, we couldn't get the data on CDAWeb that was from that one diagram. So I'm sorry, I was building this while we were flying the plane. So Mike had directed me to the paper that I directed you to, and that I was hoping to recreate that figure 23. But that data is much higher frequency than we had available on CDAWeb. So they've got like 1/8 of a second data available on CDAWeb. But then I think these spikes are similar to that.
Yeah, let's see the time scale here. So these are over an hour, and they're basically when are they happening when the satellite is close to the Earth?
One of these regions is one of these is the same as one is a zoomed in version of one of these spikes.
Yes. So I guess just stepping back for a minute. First of all, you raise a good point, Nick, that like not every data product is on CDAWeb, unfortunately. So the electric field instrument on Themis and many other electric field instruments will collect data at different rates. And because you're limited on telemetry, the amount of data you can send back, you can't always collect the like 64 per second or 128 per second or whatever to get the really high resolution spinning frame electric fields you might want. So there are modes, there are burst modes, they call them, when they do collect those data and they send them back, which may not be available on CDAWeb, but with Themis, the nomenclature is like wave burst mode, particle burst mode, and these are little snippets of data you get for like a minute or two where you have that really high rate of data collection. But then what the satellite does all the time, it sends back the once per spin every 3 seconds, and maybe also the 1/8 second during certain modes potentially. And so in order to do that, it has to do the despinning on board the spacecraft. So if there are artifacts like the electrostatic wake in that paper, it's very hard to figure out what's going on because you don't have that high rate data collected available to you to do the detective work. Let's see if you can see that electrostatic wake that's in that figure. So to answer your question about what's causing this spike or the spikes you see in here, it could be from despinning for sure. Because when you're near perigee, when you're close to the Earth, you might go into the shadow. There's a whole bunch of things. Electric field instruments for a double probe, which is what Themis is using here, are finicky. I mean, they're affected by all kinds of contamination. They're frame dependent, so you have you'll have a sudden change when the satellite motion changes near perigee. That your reference frame is changing very rapidly, basically, as the satellite is moving at a different speed. So you'll get all kinds of wacky things happening from that. But then also the plasma environment is different near the Earth, so you might get some problems with the double probe because it wasn't really designed to operate, at those very low altitudes. So I'm not sure why you have that step-like decrease, but it's probably related to one of those things I just mentioned. When you get close to to perigee near the Earth, there are just lots of changes happening very quickly, and the instrument wasn't designed to operate in that environment.
Okay. I mean, there are these interesting, I think, so I've seen this in a couple of different cases too. There are these interesting like either breaks in the data here, and you can kind of see it.
Yeah.
Oh, you can see one there too, that then appear to align with these spikes. So,
Yeah. Yeah, and so you can look at different components and maybe get some idea. So by the way, these are shown in DSL coordinates, which is it's a non-spinning frame, so it's been despun, but it's not like the typical GSC or GSM coordinates for those who work at Earth who might be familiar with. It's a slightly different coordinate system. So I have to basically what I'm alluding to is the fact that it's so strong in the Y component, those top two panels, I guess, but not in the other two, might tell us something about that. That's what I would do for detective work to figure out what's causing this, is look at why it's so strong in those components, and then maybe we can figure out. Yeah. Oh no, I guess it's an EX and EY. So let's see if we can figure out. So EX, so the top two are .0. The next panels down are EZ. EZ, by the way, another thing, DSL coordinates is the Z-axis in DSL is the satellite spin axis. And so another thing to be aware of with the electric field instrument on Themis is that there's essentially 6 Langmuir probes or voltage measurements. And in the spin plane, the plane that's of the spacecraft that's spinning, there are these 4 booms that are like each, I think, 40 meters long. So they're huge. They go way out past the spacecraft. And those give you electric fields like the convection electric field. They can measure those kind of static or low frequency electric fields. Now on the spin axis, it's just not a good idea to have a really long boom for many reasons, like 40 meters. So they had to restrict the length of that boom, and it's much shorter. And because it's shorter, it can usually only measure the higher frequency stuff. So it's not uncommon to see differences between the spin axis, or in this case, the Z component for DSL coordinates, and the spin plane components. So that's one of the reasons why I think we see the X and the Y component in DSL have these step-like or big spikes, and then the Z component doesn't necessarily have it. So that gives us some indicator that something's happening in the spin plane with those booms that's different than what's happening on the spin axis. The spin axis also has some spikes, as you can see, but they're not at all the same as the other one, as in the DSL. So I'm guessing it's something with the coordinate system we're looking at. Maybe because the satellite is getting close to perigee, there's something going on. And yeah, I'm not 100% sure what it is, but if you keep scrolling down, interesting thing will be so now you've got EFF. If you zoom in again and let me read very carefully the y-axis label.
Oh, down the bottom.
No, yeah, that's fine. So I'm reading the y-axis label there. It says EZ. So you have to almost have like a decoder ring to figure out what all this stuff means with Themis. And so there is like a the whole lexicon, and it's going to be different for different missions. But the stuff you're seeing on the y-axis there tells you something about the data product, what level it is, and what type it is. So for EZ is a Z component, DSL is the coordinate system, EFF is the I think it's fast survey, and it's a higher rate collected data product for the electric field instrument. And it's .0 tells you that they've onboard the spacecraft, or before processing, they've actually brought in the magnetic field, and they've used the magnetic field. Take the dot. Basically, what they assume that there's no electric field parallel to the magnetic field or along the magnetic field. So they use E dot B equals to 0, and they throw out the Z-axis measurement completely, the spin axis boom. And what they do is and the reason they do this is because they sometimes want the 3 components of the electric field, and they want to measure the static, not just the time varying. So they just don't even consider the spin axis measurement of the electric field, and they take the 2 spin plane measurements, the 2 components in the spin plane, and they use E dot B equals to 0. So they use the magnetometer for this, and then you can solve for the 3rd component of the electric field. And that's what they're doing actually for the Z component here for .0. All that said, I'm still not sure. The only difference I see between the bottom 3 panels and the top 3 panels is, I think, this EFF. I think if I looked at the top, it was EFS, if I'm remembering correctly. Yes. Yeah. So EFS, S means it was, I believe, spin fit on board the spacecraft. Yeah. So
yeah, that's what they were looking at. Yes.
Right. So so that tells us right there that there is something going on with the despinning process that's causing those step-like changes. So this is kind of how you can do detective work on your own to figure out what's going on. You learn what the lexicon is for the mission that you're interested in, and decode, what data product you're looking at. And then you can read about the data product, or you can contact the instrument team to figure it out. And I think we could figure out what's going on here. I don't know if there's enough time, but I think definitely it's something with the despinning, and it's probably also something related to the fact that the satellite is close to the Earth. Maybe it's the sun sensor isn't working like it's supposed to, and that's why you get that abrupt change that you don't see in the. Yeah, it could be something like that.
Okay. Yeah. Any other thoughts or questions from Mike based on the what you were looking at last night or this morning previously in your time zone groups? Okay, great. Mike and I were chatting over the break.
Oh, Nick, there's a question. Just real quick.
Oh, yeah. Yeah, go for it.
Yes, I wanted to ask about the comparison between the E12, like long and short boom. In the paper, like you, in that document, you have mentioned that we should refer to figure number 23. And in that, we can clearly see that there is a difference between whatever we get from these booms. But when we plotted that, I didn't see much difference. So like if you go to group 10, we have this figure pasted over here. And is that the case? Like we don't see the difference every time? Yeah, the first one.
Oops, everybody's there. So this one here.
Yes, this
Okay.
one. Yeah.
Yeah, I think I can answer this. So yeah, back to the. Are you asking about the difference between the two booms in the spin plane, or are you asking about the difference between the spin plane booms and the spin axis boom? Or just
No,
in general?
In general, yes.
In general, okay. So there's, and again, this is where that decoding process of figuring out exactly what data product is important, because it can get very confusing. Because like we just saw in the other example, Themis actually does make a direct measurement of the spin axis electric field with that short boom. But a lot of times when you download the 3 components of the electric field from C.web, you're not getting that. You're actually getting that approximation using the 2 spin plane booms, and then using that E.B equals to 0 to get the 3rd component. So the first thing is to figure out, okay, am I actually looking at the measured spin axis electric field, or am I getting a derived estimate of that electric field using the spin plane booms and the magnetic field measurement? So that's one reason you might not, because what was in the instrument paper for, I think, E56, which is the spin axis measurement, was actually the measured electric field from the spin axis boom. So then the other thing that comes in where you might get a difference between like different data products you're looking at for like the different booms in the spin plane. There's a whole slew of things actually. It depends on the data product you're looking at. So like we just saw EFF, the EFF data product will be different than the EFS data product. So when you're looking at, and this is common to all instruments, not just the electric field instrument on Themis or whatever, a lot of times satellite missions will, because they're limited on the amount of data they can send back, they'll process the data on board the spacecraft using some automatic processing to convert, like to do the despinning, for example, and get to a regular coordinate system like GSM or GSE. So they'll send back the low rate data that's been despun like all the time. And then occasionally they'll send back the high rate data that you can despin yourself on the ground, or you can just look at it in the spinning frame of the satellite. So that's one big source potentially of discrepancies when you're looking at differences between, like in one data product, the E1-2 might look different than in another data product. So that's that. So it's really, it gets hard when you're, I mean, the short answer to your question is you just really have to decode, look at the data product you're looking at, and then figure out, okay, what are the unique features of this data product that I have to be aware of? Is it actually being measured? Or is it being derived? And is it collecting data at a high rate or a low rate? What mode was the spacecraft operating in? So usually all of this is in the metadata, but sometimes it's not. So it can be challenging. But there's a lot of, yeah, you're welcome. There's a lot of explanations for why it could be.
Or anything else? Okay, great. What I want to do is move on to activity 2. And one of the things, so part of the goal of this whole lab was to give you a tour of CEDA web, which is pronounced differently from CEDAR web, right? With my Boston accent, sometimes I drop the I's and you get CEDA web out of it. But it's part of the heliophysics repository that is starting to grow at NASA Goddard. So part of it is to give you a flavor for the zoology of like what's available there, and when you and starting to drill down into that, as I think you've already experienced, and as Mike just mentioned, there are things like burst mode and the high quality data versus less high quality data, and which I'm not sure, you'd have to dig in and see how that's defined. I'm not really completely sure how that's defined. But then and then different binnings of the data, and so that's going to be one of the questions that you have to take some time to discuss and read through some of the materials that are there. But I think before we do that, I'm also going to be asking you to interpret some of these spectrograms and comparing them to the calculated plasma parameters. And based on Mike's talk earlier, we decided it was a good idea to spend just a few minutes just reminding people how to do that, and from what that's a part of this data chain that's happening, and how we might calculate both, first get the spectrograms and then calculate the plasma parameters from that.
Sounds good. Yeah, so I'll share my screen. And by the way, I just posted in the chat, again, data levels are going to be different by the mission, but just if you want to get the flavor of like the different levels for Themis and what they mean, there's a lot of, I think the general tip I have for anyone who's working with data, you might not find all the answers on CEDA web, but try to go to the individual mission websites. A lot of times they have descriptions of their data there. And if you don't find the answer on CEDA web, you can probably find it there, at least in most cases. So let me share my screen. And yeah, so what I want to do is, there was lots of really great questions in the earlier session. Let me just get situated here. So there was lots of great questions in the earlier session about, you have these measurements from a particle detector, and it's one thing to measure counts or whatever with a detector, but how do you get a distribution function out of that, let alone how do you get a moment out of that? And one of the reasons I think we were struggling to answer that, or I was struggling to answer that, and I wish I had put more slides on it, is it's actually a can of worms. It's a big question, because there's a lot that goes into getting a moment. And I think you're right to ask about that. And it's going to be mission dependent, what assumptions are being used in that, and how they're doing it. And also is detector dependent. But let's just go through some basics. So especially for those who haven't worked with the measurements a lot, especially particle measurements, just to give you some basics. So what I'm showing you right now is from this West ISI report that I mentioned earlier. I'm going to put the link in the chat in case you don't have it yet. You should be able to download it, although I, for some reason, having a hard time downloading it earlier, but it's definitely open and available. And in this reference, there's a really great introduction to the basics here about the different physical quantities that you get from particle detectors, and then how they map to moments and distribution functions. So physical quantities, so let's talk about these. So you're going to see a couple of different things mentioned if you look at measurements from Themis and other missions. You're going to see things like number flux, which is just the number of particles passing through a unit area per unit time. And a lot of times you're going to integrate over energy or angle. So you'll have a bin, like a certain look direction that your particle detector is facing, and it'll sample a certain angle range. like we heard about ESAs, you're going to have electrons coming in or ions coming in over a certain area on your microchannel plate, depending on their radius of curvature as they get deflected. So that gives you a number flux. But then there's differential directional number flux or differential directional energy flux. So then you start to divide things up and into per unit energy and solid angle. And usually it's measured over a range of energies and directions. And then one other thing that I should mention is total energy flux or differential directional energy flux. So usually this is proportional to the count rate. So you might ask, okay, why do we even need this? One of the reasons people use energy flux is it's a nice way of quickly seeing certain distributions of particles pop out on those like spectrograms we were looking at earlier. Because the number flux, for some, at least for the Earth's magnetosphere I'm talking about, the number flux tends to decrease as you go to higher and higher energies. So if you want something like the radiation population or the ring current population to pop out and be obvious, it's good or easier to do that usually when you look at energy flux. So there's some advantages to doing energy flux, but just be aware that there are these different quantities and they all get lumped together sometimes. So it's a little bit, and they all have different units, so it can get a little confusing. But ultimately, what you want to do with a particle detector a lot of times is get a velocity distribution function or just a distribution function. But usually we work with velocity distribution functions. So it's the number of particles, and again, sorry if some of these concepts are new to people, but it's basically the number of particles moving at a certain speed or in phase space. If you've heard about phase space before, it's a way of representing particles as a function of position and velocity. So bottom line is you're measuring particles with like an ESA or another particle detector with different energies, which are also velocities. So let me scroll down and go to moments. So why do you do that? So you have this detector. You're with an ESA, for example. Again, you're scanning over energy by taking advantage of that deflection. Other detectors will do it differently, but you're going to get the number of particles being measured per unit time and per unit space as well. Depending on how you do it, if you integrate over time with this detector. Once you have that distribution function, you can start calculating moments. And so there are these textbook definitions of moments, which you can see here, that you start with the density and then things get a little bit more abstract. But I'm going to actually go to a different PDF and show you the things that you actually usually work with, which are not directly related to the textbook definition. If you look at any textbook that talks about phase space density, you'll see those moment equations like I just showed you. But then if you look at the actual things that you want to measure, the parameters you want to work with, they're things like density, velocity, and temperature. And there's just some factors you have to add into those equations to get those parameters. And so I'm not going to belabor these things, but just know that these equations are available. They're actually in, I think, this West report at some point later in the book. But what I want to do is now jump to one other reference real quick and talk about actually how you get the moments with a real particle detector, just really quickly before we turn you loose on this. So I found this nice introduction. I'll put it in the chat. This is a paper that's freely available. And the paper itself, this is actually a nice segue from the discussion earlier about spacecraft potential and how it affects the particle measurements. This paper actually deals with that in depth. I'm not sharing it with you for that reason, though. I'm sharing it with you because section 2 in that paper has a really nice, short, succinct introduction to what you're actually doing with the particle detector to get from counts to actual moments, to things like temperature and density and the distribution function, and all of the things that go into that. And so we don't have time to talk about this, but I think there's a reason why there's an entire 600-page book on the calibration of particle measurements, because it's not an easy problem. I mean, each detector has a unique angular range it can sample, and things like geometric factors and other things you'll hear about that will basically decrease the number of counts from what you're actually expecting. So when you actually measure, I have 10 counts per unit time here, you have to actually account for things like geometric factor, basically the features of the instrument, to correct for that and say, okay, 10 counts actually means 12 counts or something like that. And so that's all folded into these kinds of equations where you, for example, are measuring the count rate. Well, this equation here is basically a starting point. So you should see the count rate related to the distribution function. And this is the what they've written down as a generalized effective aperture entrance. So it's a parameter that has to do with the details of the detector. If you go down into the more of the details here, you read about some of the other things that you need to account for when you actually convert from counts to a distribution function, and then ultimately to the moments that you're interested in. So I know this is a lot of information. I think the one thing I want to leave you with is you can always come back to these basic equations and think about and just think about what we talked about earlier, why particle detectors might not always be giving you the right answer. They might not be measuring the thing you think they're measuring. And we had a great comments about this in the last hour about how, you know, when you have artificial counts from contaminating radiation, that artificially increases the number of counts, that artificially increases the apparent number of particles. And then when you integrate over that to get something like velocity or density, you get values that are not what the actual density is. And the other thing, again, because ESAs, for example, aren't designed to measure the whole distribution function, I want to mention one last thing, which is that you know, sometimes when we can't measure the whole distribution function, we start playing games with like assumptions about what the distribution function looks like. So we measure a piece of that distribution function, and I don't know if I have an example. Nick and I were looking at some earlier, but if you think about a Maxwellian, it has some shape to it. And with the peak, where the peak temperature, I mean, depending on the temperature of your plasma, it might have a peak at a different location. You're only going to measure a piece of that. And so what some missions will do is they'll say, okay, I'm only measuring a piece of it, but let's just assume it's a Maxwellian, and then you can fit to that piece, and assuming it's a Maxwellian, you'll get the whole distribution function. So you can kind of play these games and expand your detection range of your detector, although that's can be a very dangerous game sometimes, depending on where you are and how well it will work. So there's a whole range of different ways that missions will use to go from counts per second in a given angular energy range to an actual distribution function. And it's not easy to summarize quickly because it depends on if you're spinning, it depends on the detector, it depends on all kinds of things. But that's the short intro. And I will, again, highly recommend, if you want to go into the depths in this ISSE report and some of the other references I gave are really great. I don't know, Nick, does that, or Christina, does that cover everything, or is there other stuff to cover on this? Or do you want to say anything about this?
Yeah, Mike, I think that's really good. I threw a couple of other things in the chat because, you know, again, the terminology depends on what you're studying. So, you know, for SEPs, we use flux and we usually talk about intensities, which is technically more correct for what we're doing, but in an astrophysical sense, but we actually kind of use flux and intensities interchangeably because of the, you know, how close the sun is. It doesn't actually really matter that much. But yeah, so you guys use flux and a lot of times we use intensities, but they're kind of the same thing. And then I also threw in a statement about, you know, detector response functions. That's, you know, another term that is tossed around, which may or may not, you know, is not necessarily the same thing as geometry factor. It might be that your detector only responds to certain energies or certain angles, and you characterize that when you calibrate it. You got to take that into account. And then I was just writing another comment, which was exactly what you just said, which was, you know, sometimes you only measure part of that distribution function, and so you have to make assumptions. So if we do this in the solar wind stuff all the time, you can't measure necessarily the full spread of the solar wind. And so you measure part of it and you hope you've got the peak in the important part, and then you fit it. But if your assumptions of that fitting, you know, is wrong, then you're introducing, you know, some unknowns or uncertainties. But again, quantifying the uncertainties of those assumptions is actually a really difficult thing. And I would say it's not something that's generally calculated and propagated through the, you know, the end result. And so again, you know, I loved your lecture because a lot of times you said the exact same thing I did, which was question all the data and always ask people, you know, who know the instrument, how that works, and read the documentation. But so a lot of times, you know, if you see something weird, it might be because we're making some assumption that is incorrect, but there's no real way to quantify that in an uncertainty in the absolute answer, right? And so you'll see that's a lot of times people just sort of throw on an extra uncertainty factor just sort of to cover it. But we don't really, it's really hard to quantify those things. And I see Nick smiling, so he's just
well, I hope
entertained
we're
by
not.
something.
I feel like we might be creating an existential crisis, like because you
Yeah.
also said like unless you validated your models with data,
This
I
is true.
really don't believe them. But then you really have to.
All right, in my defense, I've seen people who have simulated situations, created a model, and then used the model data to validate the other part of their model. And I'm like, okay, that's not validation. That's just like, Ouroboros or something. You're like eating your own tail or something like that. Sorry, B. Joyce got a question.
Yeah, hi. Actually, in yesterday's activity, we have seen that depending on the state of the instrument, the geometric factor actually varies. Now, my question is, when the geometric factor or G value varies, what exactly varies? What is, happening there? Is it like physically changing the aperture of the instrument or so, or only the response function or the response time of the instrument, etc.? So I'm literally
I'll
curious
answer
to
this
know.
I'll answer this for the SEPs, and then Mike can probably address it for other instruments because it's done for different ways. There's different ways you can do it. So the instrument that you guys were messing with, looking at the data for, we don't physically change the aperture, but what we do is we turn off parts of the detectors to effectively change the size of the detector that is measuring protons and helium, but let's just talk about protons. So now you've got a bigger detector, but the outside ring of it is basically insensitive. So you've sort of made the equivalent of changing the size of your detector to make it smaller. And so that's what the geometry factor reflects. The geometry factor is usually a measure of kind of how physically big your active part of your detector is. There are other instruments, and I didn't mention this in the the very fast discussion that I had yesterday. But there's an instrument, they do it one way on ULICE on ACE, and they do a slightly different way with the same type of instrument on Solar Orbiter, which is a time of flight instrument. And the way they handle it is they've got a physical door. So on ULICE, they've got an actual door which comes over and covers the actual opening of the instrument to different degrees, depending on how intense the event is. And so that physically, makes your aperture smaller. Now, the problem is that with ULICE that they found out is since you've got a square opening and you've got a door here, you've got lots of weird effects coming in from angles and stuff. So they changed that on Solar Orbiter to make it an iris. So it's actually an opening that's more round, and it kind of contracts just like you would with your pupil or something. And so depending on the intensity, it will actually physically come in and cut stuff off. So there's different ways of doing it. And I'm sure in the magnetosphere, you guys have other ways of doing things. So maybe Mike can talk to that.
No, I think you gave that's basically it. There's all kinds of things. I don't even know. So I'm definitely not an expert on this. And I think the geometric factor is one thing. I don't know, Christina, is part of it, for some detectors at Earth, we also talk about things like dead time. So over time, the instrument ages. Is that factored into the geometric factor, or is that yet another factor that's separate?
That's another, so that's another factor, and that usually comes into the live time that we talked about live time earlier. So live time and dead time are kind of two halves of the same thing. There is time periods where the instrument is processing and it can't do anything else, right? So that's what we call dead time. And so the time periods where it can do other stuff, we call that live time. There are aspects of that can age, and so we usually try and always have a measure on board of what the live time is so you can correct for it. And then there's other things where detectors themselves actually age and they become less responsive to, say, the energy range, which is like your detector response function. It could be that initially when you built it, your detector was really good, it does it has very low efficiency for, say, a 1 MeV particle, but it does really great for a 10 MeV particle, and the response function looks nice, like a sort of step function. And then as it ages, that kind of sags. And so now your efficiency at 10 MeV, which used to be near 100%, has sagged down to like 70% or something. And that will start affecting how many of those particles at 10 MeV you can actually measure. And so you have to factor those things in. When they're nice step functions, then you're just like, it's all good here and it's nothing here, but it rarely stays a step function. So you have to worry about those kind of efficiencies. So, and then I will just throw this in because somebody asked if the geometry factor changes with time in terms of an aging, and technically no, but I will say that the instrument on ACE, which is CIS, which I talked about, had strips on 2 sides of the detectors. Those strips are in, they're independently read out, so you can get the exact location, or pretty, a pixel of where the particle went through on the detector. We've actually had certain strips go noisy, and so we've turned them off. And so effectively that part of the detector is now dead, and that will actually change your geometry factor. So they're actually sort of misstated that incorrectly, is that you can have, that's only because we have the individual strips and we can turn individual parts of the detector off. But that would be the way you would change the geometry factor, because now not the whole detector or all the strips are active. Now, like, only 80% of them are. So now you've kind of effectively reduced your geometry factor by a certain amount. So that's why we always have to like kind of go back and, as these things age, kind of fiddle a little bit with all these correction factors. And I'm sure in the magnetosphere, this kind of stuff happens all the time, because you guys are experiencing all kinds of radiation effects that can cause problems.
Yeah, absolutely.
Thank you, Krishna.
Yep.
Sure.
Yeah, absolutely. I just remembered there's one other thing I wanted to mention about the distribution function that I kind of alluded to. Even with a single instrument like ESA on a single satellite mission like Themis, there are different modes of operation depending on where you are, and if there's something interesting going on, you might enter that thing like burst mode we were talking about earlier with the electric field. And this is something, again, that gets really challenging because let me see if I can find it real quick, but there are all these different data products available to you on C.Web, and you will see this in your activity probably, that there's going to be so many different options for loading ESA moments.
And that's actually the first exercise in the activity too.
Oh, good. Okay, so maybe I won't give it away.
Don't give away the answer.
Yeah, but
well,
there are.
I think I will let them explore that, and maybe you can comment on the different when they're done, you can comment on the different data products. So yeah, so let's move over into the activity. I do want to. We've used some time here to review some stuff, but I want to give you about 40 minutes, I think, on the activity. So between 30 half an hour and 40 minutes to go into the activity. I'm posting the mural board, so the activity is posted there. I'm posting the mural board, and we'll use the same synchronous rooms that you used yesterday, and we'll be around to do that. So off you go. Shoei, can you make Mike a co-host so that he can move around and talk to groups as they are starting to work on this?
Sure. Also, I'm sure you'll all figure it out when you get there, but the elves were busy again last night and things are not in numerical order, so.
Okay.
And I have the list if you don't know what group you're in.
Nick, just because I'm toggling, I have Slack on a different device. Can you put the mural board link in the Zoom chat as well for me?
Sure. There's like nothing on it right now, but
Yeah, no, I know, but eventually. Thank you.
And Nick, just a quick question: the deep space instrumentation thing, did you find it in Kippelson and Russell? I was trying to scroll through. I couldn't figure out if it was just something they had in their lecture notes, or if it was something that actually was in the Kibbleston and Russell textbook.
Which I'm not sure.
Okay, I will double check that, and if I don't find it, I'll let you know.
I don't think so. In my recollection of, so I'm not sure what you're asking about.
It was just a question in the chat. There was I flashed up the deep space instrumentation where they had the short summary of like what a Faraday cup is and a distribution function. And
I don't believe that's in Kibbleston and Russell.
okay, I'll try to dig up a reference.
They've got the distribution function that you found, but yeah, it's not. I don't think they cover. Right, they don't cover instrumentation in Kibbleston and Russell.
Okay, got it. We'll dig that up. And I'll be right back, actually.
Yep. Hi, Harley. How you doing?
Hello, sorry, just struggling to get to the breakout room. I'll get that
Okay.
sorted now. Just wait. He says.
And I told you where to go, right? Oh, he's gone. Never mind. Wow.
Oh, he's back.
Yeah. Hey, Harley, what happened? Nope, he's going to a room. Okay. I think.
It looks
Oh.
like he's in group 13, right?
Yes, right. That's
He
fine.
just show up. He hasn't been logged in all day.
He was here this morning.
He was.
He was, yes.
Okay, because he hasn't been here the rest of the week.
Right.
And I didn't see him this morning.
I communicated with him and he's apologized, but he's here now. So
Okay. Well, I know he's been sick, so.
yeah.
All right, so it looks like group 11 only has 3 people in it. And let me see why that is.
I think there's a few that only have 3 people. 3, 4, and 9, and 11.
Group 11 should have 4 because I think other than Pawan Kumar, everybody is here.
So they have Alex, Murdy, and Eduardo. Who are they missing?
Oh, did Sasha and Reddy not come back after break? Because Sasha should be in that group also.
Yeah. I don't see them.
Yeah, it looks like
on
Sasha
the
hasn't come-
participants. Yeah.
Yeah, it looks like they probably didn't come back from this morning.
I think this morning we had like 63, 64 or something.
Well, I mean, that includes.
And of course we had, yeah.
I think the really positive thing is we've had no drop off.
Yeah, it's been pretty high consistently. Yeah.
Students haven't been decaying.
That's good. How many are actually going to be in Boulder?
Only 25.
26.
26.
I thought we lost somebody.
No, we lost a virtual person,
Oh, I see. Okay.
but no, they were found. Sorry, sorry. I keep talking about with Shelley about missing students, and I'm like, no, missing from the sessions, not in general.
Like, don't put out any milk cartons.
No cereal boxes, no milk cartons, no. Sorry. Yeah, 26.
That's good.
Okay.
It's gonna be a really nice group.
Well, we'll find out when we're there. But based on this, my dirty little secret is I've been trying to put I've been trying to spread them out, which means that there's roughly 2 of the in-person people in each group. Out of the 4 or 5 that we have in the breakout rooms, so that they're starting to meet each other, but also like they're not all, segregated into one room.
Yeah, that's a good idea.
Yeah,
It's a different kind of jigsaw activity.
Yeah.
It's your jigsaw, Nick, to like try and figure out, all the different permutations and what you don't want to combine and what you do. And
well, right. Yeah. So I one of these days I'm going to write some code to do this, but somebody, I still have to, I haven't wrapped my brain around pivot tables in Excel yet, but
artificial intelligence, man. Just ask ChatGPT what they would do.
ChatGPT. Well, the thing is that you need the data to be clean.
Yeah.
And sometimes it's not always as clean as you'd like.
Yeah. Mike and I are familiar with non-clean data, I'm sure.
Yeah. I wonder what would happen if you asked ChatGPT to write the lectures. Like, what would it come up with?
Yeah, that's a really good question.
Summarize.
I was actually told in a call that I had yesterday where we have to write a report that somebody said, okay, well, if you've written stuff and you need to shorten it and condense it, it actually does a really good job if you feed that to ChatGPT and ask it to basically sort of summarize it. I mean, obviously it doesn't get it perfect, but it actually does a pretty decent job of fixing it up.
You could write an AGU abstract that's too long and feed it to ChatGPT and say, hey, I need this to be fixed.
Exactly.
Nice.
Exactly.
Well, the joke about is there a doctor on the plane? Right.
Like which kind of doctor?
Well, and then the add-on is that, as the stewardess says, it comes up to you and says,